for the reinforcement. Innovation is the theme of our new systems, considering the safety, efficiency, and upgrading demand of prefabricated parts. Sorry, what is happening? Okay, we decided to standardize prefabrication with both horizontal and vertical frames with both connections placed linearly along the frames for less tolerance concern, higher construction speed, and upgrading support in the future. The sewage treatment system is innovative based on the local conditions of Tibet. The system utilized a multi-layer biofilter due to the low air pressure in Tibet Plateau. The artificial wetlands selects local vegetations with higher capacity of sewage treatment. HVAC system, lightnings, and plugs are selected based on the principle of efficiency and economy, which is expected to have less load for the building. Here we featured economical combination of air source heat pump, underfloor heating, radiator, and fresh air machines for the HVAC system. The LED lightnings for both interior and exterior space, and efficient plugs machines. Our envelope design is based on the existing condition. After site visit and simulation, we identified 5 key issues. The R value of the existing envelope is even not reaching the standard. Consider the problems we identified. Our goals of the envelope can be elaborated into 4 points. Renovation based on the existing building, use local materials, ensure the high performance of the envelope, and the envelope for a higher durability. Resiliency of the envelope is our primary concern. Sangha is in climate zone 5C with the climate risks of drought, frost, and snow. Based on the existing envelope, we arranged air thermal and moisture barrier to ensure the envelope to resist vapor, air leakage, and low temperature. In terms of the material, the project proposes a hybrid utilization of straws as decoration board and insulations. This insulation can be both permanent and temporary on site. Permanent straw insulation board can upgrade the insulation to R value of 21. For the temporary ones, we propose the seasonal edible insulation bricks, which can become insulation in winter and feed livestock in summer. Other than improving the existing envelope, the solar corridor is also important for the overall passive design of the building. For the envelope of the corridor, we proposed the quadruple glazing glass. It's actually 2 pieces of glass plus 2 high-performance heat shielding films, which tremendously transform the thermal performance of the building. Passive and active technologies both have much concern with the efficiency of the building. In this project, our design is conducted in a sequence so that the HVAC system will not overwhelmingly perform. We firstly prioritize the optimization of passive technologies for less energy loss. Then we have HVAC system to compensate the energy loss and achieve comfort. And finally, the solar system to offset the energy consumptions. When we have the envelope system involved, the energy loss from the building is minimized. The EUI is lower to 85.74 according to our calculations. We definitely want to use HVAC system with technically the highest efficiency. However, in real perspective, the economical situations and resource availability always pose a handicap to the design decisions. Based on our concern of maintenance as well as operability, we finally selected air source heat pump with underfloor heating for the children's activity zone, while radiators applied to other service area to control the budget. Ventilation system is designed with heat recovery only with zonal regulations. And the final stage, we introduce the PV system for less environmental impact. We calculated several versions of PV arrangement, and we finally decided PV panels to orient towards west and east with 20 degrees of tilt, so it can generate more electricity than the other versions. When we have the passive design HVAC systems down, EUI could be 37, which is lower than requirement of 48. And when we arrange the PV panels on the solar corridor, the EUI with renewable energy calculation can be lower to minus 25.74. Other than the less environmental impact of solar systems, the resiliency of the system is also a concern for the project. Tibet might have very heavy snow in winter, so the PV panels has a spacing of 20 centimeters between each, and a 500 millimeters high bracket are also added below. For grid outreach, we developed 4 modes to assist the building to function well. Here is the energy supply and demand chart. We understand that cold areas like Tibet is facing a situation that in winter, the energy consumption is extremely high. But in spring and summer, the consumption turns very low because no cooling load is required. In this situation, our goals are to offset annual energy consumption of the year, and the calculation of the energy consumption is in a very extreme situation, in which the kindergarten is operating all days without summer and winter holidays and weekends. To make sure the PV panels is safely and softly interacting the load, the grid, and the batteries, we also developed a logic for the management of charging and discharging. Other than the use of clean energy, which has less carbon emission, a couple of design decisions we mentioned before all contribute to the reduction of carbon emissions. After the calculation, we reached the result that inverted carbon emission has been lowered to 391, which has reached the level A for the assessment. We consider the reduction of carbon through PV-generated electricity. We expect that in 7 years, the project is able to achieve carbon neutrality. We can say that we reduce carbon emissions to strive for the well-being of the environment. But what are we doing for the well-being of occupants and community? Our comfort measurements includes the use of high-performance shielding films for light control, as well as the material selected for improved acoustic environments. Safety of water contribute to another concern of the health. The consider for safety is in both the water supply and drainage. For the air quality, we have source control and pathway control ensured. And at the end point, control system is set up for effective control of active system, light, and air quality when undesirable circumstances happen interior. For the well-being of Sangha community, we identify 4 demands that Sangha village is urgently needing. Rather than having the Koja building a space privately tailored to kids and kindergarten staff, the kindergarten is expected to open to the member of Sangha community when after school time and during holiday time. The comprehensive utilization of straws will help to transform low-income traditional industry. The production of clean energy will be able to serve more surrounding families and facilities, which makes profit for the kindergarten facilities. In terms of potential risks, noise and cooking fumes might be the risk as the project implemented. Hence, the function layout are carefully arranged with the consideration of windmills. Water pollution is a problem that Sangha village has for a long time. As the Koja building revitalized and the intensity goes up, we introduce a sewage treatment facility for the neighborhood. Finally, let's go back to the start of presentation. We understand that still significant amount of villages like Sangha village is in urgent need of kindergarten construction and village revitalization. We proposed standardized prefabrication modules for buildability. The modules allow for further alteration for scalability, and we eventually expect mode of kindergarten construction promoted to more traditional Koja building across Tibet. Besides the wide promotability, we witnessed a couple of technologies empowered our construction mode, and each of the technology is expected to promote it to different Tibetan villages. Overall, the budget is being shown below. It's being estimated to have 6,600,000 Chinese yuan, which is near the average construction cost of Tibet in China. Our team SolarArc is striving for the sustainable future of China. Through this competition, we are able to construct a network between research academics and enterprises to provide real-world perspective for our project, for our research, and for the students' growth. Thanks all of my teammates for the hard work, and thanks to Decathlon for this wonderful opportunity for the presentation. Thanks, everyone. Please feel free to scan the QR code. We have a website for our project.
Thank you so much, Southeast University and Tibet University. You did an excellent job presenting. I'd like to now open it up for question and answers. Can I hand it over to the jurors for their questions?
Yeah, sure. Tell me a little bit more about what you learned about the orientation of your PV panels. I see how you looked at different either flat 20-degree angle and then also the east-west. When you modeled it though, inside of the chart, I just see the simplistic chart. Tell me a little bit more about your findings from modeling the PV orientation.
Yes. Please allow me to go back to the page of our simulations. Because we are in Tibet Plateau, the altitude is really high. So we witness a situation that in the sunrise is really early, but for sunset, it goes very late for the Tibet Plateau. So here we are modeling on the western east because it can have more contact in the sunrise and when in sunrise and when in sunset, the western east orientation can have more time for the jet PV to electricity generation at that time. Actually, we expected that the southward will be the most electricity at that time, but in fact, this southward simulation is a very extreme condition because when you have southward or simulations, you have spacing between each of the PV panels because you cannot have a PV system that is all the way like a very smooth one that from the very start to the end. So it will be a really height for a very dramatic height for the PV system. But in this situation, we're just simulating on that situation. And we found even in this one, it cannot generate enough electricity than it's in west and east. So our final decision is that we decide to use that in the west and east for our PV panels.
But don't you have plenty of roof space? I see lots of extra roof space that you could have put PV on.
Right. We actually have a lot of thinkings about the PV panels because always like in Sangha village is a very poor condition. And usually we understand when we have more PV panels, it has a lot of, you have to spend a lot of money because for the energy performance, it doesn't mean that you have more PV panels, you have the more efficiency of the project. So we encounter a situation like in most Tibetan areas, like in high altitude, for most of the projects, when they have more PV panels, they cannot offset their energy consumption in summer. Because always like, let me talk about an example in here, like in, when we have more PV panels, it might have stress for the batteries, but the battery is not efficient enough for the project. We have to, like the technology of batteries is not quite mature at this time. So it's really a problem. And you have to contact with national grid. But if you have generated over much electricity at that time, it means that the national grid will not respond to you, like having enough electricity sent it to you when you have over much electricity generated by yourself. So when the disruption happened in summer, it cannot respond to you when the national grid is not serving to you because the national grid will not serve to you at that time. So we think that more PV panels and more electricity, the batteries is not a very efficient way for us to doing in this project. So we actually think quite a lot about that. And we simulated that in a very extreme way because for the winter holidays in Tibet, it's usually from the mid of November to the end of March. But for the summer holiday, it's very short. It's only from the mid of July to the mid of August, only 1 month. So because we are sharing that with the community, so we expect that some of the spaces might open. We have that kind of simulations here.
If I might build upon this, and these can be very short questions. You're not required to explain everything for me, but okay. Was any consideration given to including wind power in preference or in complement to solar? And you don't have to explain, but was that considered?
We actually have some experience on the wind powers because very small scale wind powers is not stable at all for the building. It might crash the whole system when the wind is overly high. So It usually happens when we have more wind systems being installed across the whole community, so it can have that effect. So usually we are not considering about this wind system for our design. Always the solar systems is most appropriate one.
Understood. And then second question, lots of attention was paid to building envelope. And I think it's very challenging to have an unstable existing envelope now integrating with a new envelope. So 2 questions. Would this process work without existing buildings? Was that how you did your analysis? And did you include building performance analysis with the existing buildings? And then also as a model where it was all new construction? Does this make sense?
Can you briefly explain about that? Because we have the simulations on the whole one, like for both the corridor spaces and
Did you make a model, a simple model even, where it was all new construction, so you could have an optimum mass wall construction versus the existing wall construction?
right. We did that in the carbon emission one, because like well, let me switch to the carbon calculations. Because in this one, we are doing the retrofitting calculations right here. That means that when it's in very new constructions, all the carbon emissions will be happening. It's like in the left one, is the left, the blue one. But when it's all being a new construction, the retrofit, the carbon emissions might be quite different from the left one. So
Thank you.
Could you go to that slide that shows generated energy versus building? Yeah, that one. No, that one. So did you at all consider trying to match the PV output to the energy consumption?
we have,
And if so, or if not, why not, or why did you?
okay. Because we think, firstly, we are not expecting to have more PV panels at our project. So we quite keep a very tight constraint on the PV orientations and PV spaces we installed. So I think the most appropriate spaces for us to install the PV panels is the corridor space, the roof of the corridor space. So we are trying to maximize the PV generation on the corridor spaces. Let us not talking about having PV panels on the existing buildings. And we have that result at the next stage. And we found that, oh, even in this extreme condition, it can still nearly offset all of these consumptions and productions. So we have this decision showing all of them to you, because we're very honest with the real situation that is happening for this project. So here is the real situation that's happening. And why is in February that is being lowered down? Because we consider about the Lunar Year Festival for China. But the winter holidays, we are not thinking about that in that situations.
So is the grid pretty robust? So like in the winter, when you're short on energy, you can just pull energy off the grid. Is that the thinking?
Sorry, can you?
So like January, March,
Oh,
November, December, you're not generating enough energy on site, right? To offset the energy use of the building. So is the grid pretty robust, or, you know, I don't know how reliable the grid in Tibet is. But so my question is the grid pretty stable, so you could count on getting energy off the grid on those months that you don't have quite enough energy, or do you need to find ways to use less energy?
we actually have the site investigation at that time, and in real situations, the grid is strong enough at the site. And in the real situation, I mean, it's in a very extreme situation. The real situation is that the energy consumption could not be that high in that situations. So this is what we intentionally did for the simulations right here, because it's not like for design things that we're trying to solve, is also an area of research, because like batteries, all of this stuff might be the problems for the like extremely cold areas like Tipi Plateau. So here we are pretty sure that the energy supply and demand is stable. And in winter holidays, it cannot be that high for the energy consumption at that time. So we are trying to showing that not only for the real situations, but also showing all of the juries about what is exactly happening in the extremely cold conditions. And we are still striving for the research, for the battery technologies, all of this stuff for the future.
I was
Do you have
going
a
to
question?
switch topics. if
Okay,
you-
go ahead. Oh, well,
Um,
I'm switching topics too.
Okay. Can you tell me more about the seasonal edible shelters? I think using the hay in the envelope is very interesting, but I'd love to learn more about how that functions.
Okay,
Me too.
seasonal edible ones.
Oh,
A little quickly, because I have one more
Okay,
question.
because like in Sangha, they have a lot of straws like being in a circle, but for like it usually as the food for the livestock. But we want to improve that the thermal capacity of the building. So in winter, it's like very less the rainfall and it's very stable right there, and it's close to the farmland. So we decide to use like to have some productions on the straws and to make the envelope of the system perform much well than in the summer. And in summer, it can be removed away as you wish and to feed the livestock in the situation, because the agriculture is the primary industry in there, and they have large productions of the straws right in there.
So what does the maintenance look like for that, and how do you go about like the change of adding straw? when you need
Because
it?
yeah, we have very simple machines like for manufacturing all these materials, and it's currently very easy for the locals. And so we decided like when you manufacturing that, you can definitely store that in the storage, but you can place that beside your buildings to improve the thermal functions. And when you remove that in summer, the thermal and the air and all of this earth will function quite well in summer to help them to function in that location.
Great. At this point, we're at the end of our Q&A session. I'd like to thank Southeast University and Tibet University once again. Great job answering those questions. Next up, we will have National University of Sciences and Technology. I invite them to come up front, and we will start with their presentation at 9:40 a.m.
thank you.
Yeah, sure. We are here.
Hello everyone, can you hear us?
Find myself in these institutions.
Much better.
Yes.
All right. For National University of Sciences and Technology, I believe you all are remote. Can I request all the presenters to turn their videos on and just state your name so that we can test your audio?
Yeah, hi, this is Zed.
Yeah. Hi, this is Ranjit Kumar.
Hi, I'm Kainat Tariq.
You did.
Yeah, that sounded good. I believe we can hear you now.
We have another member. We'll ask her second.
All right. So I believe we have the three presenters. Have you all stated your names and made sure your audio works?
Just give me a few seconds. We have 4 presenters.
All right. I'll wait
Hello.
for the presenter.
Yeah.
Hello, this is Aisha.
Yes, done. Now we are done.
All right. Is the fourth presenter, is their video on as well?
We'll just ask her.
Yeah, because I would like to spotlight the presenter on the screen.
Divya.
Is this, can you
Yeah,
unmute
okay.
yourself again?
Aisha, please acknowledge.
Hello, this is Aisha.
Great. We can hear you all and also see you on the screen. You may now start your presentation. Good luck.
Pardon me. Can you turn on closed captioning, please?
Can we begin?
Yeah, I turned it
Yes,
on.
can you please start?
On.
Yes,
Yes.
please start.
Okay. Good morning. We are delighted to represent the National University of Sciences and Technology from Pakistan at the Solar Decathlon Competition 2024. We are going to present a retrofit design proposal for the NUS Creative Learning School. Our team consists of individuals from various backgrounds, bringing a rich diversity of perspectives and expertise to our project. Here you see the content of presentation. Nestled in the heart of Pakistan's capital, Islamabad, the NCLS building proudly stands within the National University of Sciences and Technology, situated in the vibrant educational hub of H12 sector. Surrounded by esteemed universities in H13 sector, it serves as a melting pot of knowledge, welcoming students from all walks of life. Our choice of location reflects our commitment to education's broader community and accessibility. Islamabad experiences a humid subtropical climate with distinct seasons, spring, summer, autumn, and winter. The hottest month, June, sees average highs exceeding 37 degrees Celsius. Understanding these temperature fluctuations is pivotal for our retrofit project. Dominant wind directions include northeast, southeast, and southwest, influencing ventilation, solar exposure, and overall comfort within the building. Monthly diurnal averages reveal low diffuse radiation and ample sunlight throughout the year, with maximum solar radiation in summers and a slight dip in July and August. High thermal lag and winter temperatures below comfort zones necessitate heat retention strategies. The building's orientation exposes it to maximum summer sun from the southwest and west, warranting a shading device on the southwest facade to mitigate heat accumulation. The Capital Development Authority, which is CDA, plays a pivotal role in Islamabad's development, ensuring growth and modernization through strict building codes. The building, due to its recent construction, adheres to all the standard building codes. Education should be more than just books and classrooms. Our retrofit project is guided by the belief in a balanced approach, blending nature with nurturing. By integrating sustainable design principles, we aim to create a healthier, more inspiring environment for students. We aim to reimagine education where nurture and nature coexist for students' well-being and environmental sustainability. With classroom and circulation spaces dominating our two-story building, our focus lies on enhancing comfort and functionality. By addressing heating and cooling challenges, we aim to create conducive learning environments where students thrive. Through thorough analysis, has identified 5 major issues impacting our building. Our goal is to address these challenges and foster an enhanced educational environment. Now, to tackle the identified problems, we have developed practical design strategies focused on improving ventilation, creating social spaces, and reducing energy consumption that will be elaborated as we progress. Our first design strategy tackles the issues of dead corridors and focuses on revitalizing dead corridors. These neglected areas marked in blue offer significant potential for transformation. Additionally, the areas highlighted with red circles signify potential zones for air leakage due to louvers. Addressing these points is critical for improving energy efficiency and advancing our goal of a net zero carbon building. Our corridors embody sustainability at its core, designed with a focus on 4 key principles. These spaces have been transformed into models of efficiency and connectivity. Dead spaces have evolved into bustling social nodes, promoting interaction and collaboration. Louvers, once open to air leakage, are now tightly sealed via silicone sealant application along the seams and joints of the louvers, enhancing energy efficiency. Innovative socializing nodes strategically placed under staircases and at corridor ends encourage engagement and community bonding. In every aspect, our corridors reflect our commitment to a sustainable future. Our next architecture intervention focuses on designing a green atrium, reimagining an underutilized central space. This revitalized area serves as a vibrant community space, fostering uninterrupted circulation for students while encouraging social interaction. The green atrium contributes to improved air quality, natural cooling, ventilation, noise reduction, and provides a much needed socializing space, enhancing overall learning experience for students and faculty. Our next target for intervention is the roof, a significant contributor to heat buildup within the building. Following a user survey revealing following a user survey revealing notable temperature differences between floors, we propose 3 main interventions: solar panels, a roof garden, and a solar pavilion. The extensive roof garden offers a feasible solution, utilizing the otherwise unused space efficiently with its lightweight construction and minimal maintenance requirements. The green roof system consists of multiple layers, including soil and vegetation. During the cooling season, it lowers peak indoor air temperatures by approximately 7 degrees Celsius. Moreover, the playful roof covering doubles as the solar pavilion, housing glass paneled solar panels. The double roof structure with an air cavity in between facilitates natural ventilation, reducing reliance on mechanical systems and energy consumption. Material choice is recycled plastic lumber, which offers sustainability benefits in resource conservation, energy savings, and longevity. Its durability and resistance to environmental degradation make it a viable choice for outdoor pavilion, contributing to a more sustainable built environment. The next slide outlines our roof garden's technical aspects, focusing on cost effectiveness, ease of installation, strength, and durability. Please can you change the slide? Ensuring optimal performance and sustainability without compromising quality. This approach results in a robust, functional, and visually appealing environment. Next slide. The existing facade compromising solely of bricks lacks additional insulation, resulting in excessive heat gain within the building. Through meticulous design intervention, we have transformed the building's facade for optimal performance via rain screen cladding system. This innovative system features an air cavity ensuring continuous ventilation and mitigating excessive heat gain, compromising a robust structure for polystyrene insulation and travertine cladding. Renowned for its resilience, the solution reflects and regulates heat effectively. The chimney effect within the cavity further stabilizes interior temperatures, enhancing comfort year-round. Moreover, the system minimizes condensation, boosts material durability, and augments thermal and acoustic insulation, elevating indoor environmental quality and reducing energy consumption. Next slide. To effectively tackle solar heat gain and optimize energy efficiency, our proposal. Please can you change the slide, Zed? Now, to effectively tackle solar heat and optimize energy efficiency, our proposal centers on implementing a shading device system specifically tailored for the southward facing facade. Unlike conventional dynamic shading systems, which rely on electricity for continuous angle adjustments, our innovative approach harnesses the power of buoyancy. By incorporating a buoyancy-driven mechanism into external shading device equipped with horizontal panels, we significantly reduce energy consumption. Additionally, by referring to the reception of solar radiation to maximize daylight availability, we can achieve a quasi-optimized movement mechanism for the blind slats. This mechanism initiates the rotation of the blind slats through linked horizontal pivots exclusively driven by a buoyancy force. Our design showcases the driving and rotating mechanism of the panels in various directions, along with the detailed configuration and frame design to support the shading device. We've assumed that the building slats rotate from horizontal to vertical position every 6 hours during occupied hours. This strategic adjustment optimizes solar radiation reduction, particularly in the southeast and southwest orientation, resulting in an impressive 56% reduction rates. In cohesion with the application of infrared reflecting coatings on the windows to reflect back the IR part of the light for heat rejection purposes, it will contribute significantly in the reduction of heat gains. Now the landscaping. Please, can you change the slide, Zia? Permeable pavers in the playground manage stormwater sustainability, reducing runoff and enhancing safety. They combat the urban heat island effect by cooling the area through water evaporation and improving water quality. These pavers enhance aesthetics and longevity, embodying an eco-conscious urban development approach.
Aisha, can you hear?
Aisha, please, can you hear?
We can't hear the speaker if they're trying to speak right now. Are they
Just a
unmuted?
second. Aisha, can you?
Please
Aisha,
unmute
can you please
yourself
start?
before talking.
Here is the base case of our project. So, can you hear me, please?
Yes, we can.
Yes, yes.
So here is the base case of our projects. Next slide, please. Please, next slide. Our goal with the HVAC optimization was to make sure the air inside our building is clean and healthy while also using energy more efficiently. We followed standards, ASHRAE standard 62.1 to ensure we did things right. A pivotal aspect of this initiative was the deployment of the cutting-edge heat recovery system. The decision to opt for an around heat recovery system over other options was driven by several compelling reasons. For example, the RACs offers lower utility payments and quick payback periods. Moreover, they boast a range of the benefits, including lower energy consumption, reduced investment for heat generation and distribution, and minimal environmental impact. Other than this, what sets our selected heat recovery system apart is advanced design, featuring a detailed separation of air streams. This design ensures that the outgoing and the incoming air stream remain distinct, completely eliminating any possibility of cross-contamination. So the HVAC implementation and the outcome comes with the heat recovery efficiency of this system is around 50 to 65%. So we set up efficiency of 60% with the system of the Red Screen software. But we did not stop there. We took a proactive stance by implementing a dynamic scheduling approach for fan and ventilation control in the proposed phase. This approach tailored to occupancy patterns and space utilization within our building, optimize energy usage without compromising on IA. Furthermore, with the assistance, with some additional cost, we made a switch to a better kind of the coolant for our air conditioner. Red Screen facilitated for our transition from HCFC 22 to HFC 32 refrigerant, offers immediate benefits. For example, the global warming potential of HFC 32 is very low. HCFC 22 has a global warming potential of approximately 1810, which is very huge value, while HFC 32 has a much lower global warming potential of around 675. So in this picture, you can see that by utilizing Red Screen, we enhance ventilation, implement dynamic schedulings, and embed HVAC improvement. We have not only achieved tangible financial benefit, but also contributed to a cleaner, healthy environment for our occupants by reducing the CO2 emissions.
Thank you, Asha. In the lighting section, we have considered basically 3 goals: equipment comfort, sustainability, and energy saving. To achieve these goals, a thorough analysis of lighting has been conducted across various spaces within the school, including offices, classrooms, science labs, resource lab, library, computer labs, exam halls, and even in bathrooms. By transition from a traditional linear fluorescent tube to energy efficient light emitting diode, we have substantially reduced the amount of energy contributed to schools' overall sustainability objective. Furthermore, the illumination level of each space was considered according to ASHRAE standard 90.1 to provide comfort to the equipment, as it was one of our goals. Special attention was given to the classroom and library lighting to ensure student well-being and maximum performance. The table shown here in the slide summarizes the annual lighting load of base case and the proposed case. As you can see that more than 70% of the energy can be saved by changing the LED lights. Now I will hand over to Mr. Zaid, who will present about the other scheme
Okay.
software,
Hey everyone,
result, and other
so
concept
we have
criteria.
Hey everyone, so coming towards the PVC deployment, a detailed techno-economic assessment was made utilizing an Oriel developed software system advisory model. It was analyzed in the market available solar PV panels were analyzed for the feasibility over here in our simulations. The market available solar PV panels, which were bifacial in nature, were used both on the pavilion as well as the rooftop. A total of 98 kilowatt of system was analyzed using NREL software. A total of 1,66,000 kilowatt hours of generation is calculated for each year through our proposed PV system. A total of 0.5 acres of land is required for this deployment, which was tailored on the solar pavilion as well as on the roof. This system is highly feasible with a positive net present value and a payback time period of around 1.5 years. The levelized cost of energy for this system is around 1 cent per kilowatt hour, which lies in the national range of electricity production. Moving forward, coming towards the grid interactivity, in the second stage, the dispatch of PV system was optimized with the objective to peak shift the demand from the grid during peak school times. The blue line in the graph shows the electricity from the grid, while the orange line shows the electricity exported to the grid. As you can clearly see, the blue line clearly shows that a significant peak shaving from the grid demand is observable. Moving on, coming towards the carbon impact of our system, the environmental analysis was conducted using Red Screen software. And a net operational, reduction of 93% carbon emission has been calculated. I'll try to summarize it as far as I can. Coming towards the retrofitting cost, a total of $4,460 of retrofitting cost has been calculated for our retrofitted design, among which around 70% of the cost goes entirely to the solar PV system, then towards the solar pavilion, and even for the solar power heater, lighting and contingency
All
makes
right.
around the rest of
Unfortunately, we're at time. I would need to stop you right
Okay.
there. But thank you so much for presenting. You all did a wonderful job, a very detailed presentation. I'd like to
Thank you.
now open it up for question and answers. I'll hand it over to the jurors.
I see under your HVAC section that you talk about refrigeration, the refrigerant selection, that you also talk about tonnage, you also talk about your emission savings. Did you as a team proceed all the way through to potential equipment selection, operations, understanding, control strategies, et cetera?
And just a second, we'll be answering you just a second. Aisha, can you please answer?
I'm sorry, I missed what he said.
Just a second. Well, can you please come again? I guess we are having some internet issues over here right now.
So my
Can you repeat the
question
question?
goes back to,
Mm.
I see tonnage. I see refrigerant selection,
Mhm.
and I see initial calculations. Did your team progress all the way through potential equipment selection, operations, and even control strategies?
No, we
Yes,
can't actually.
I
We have
yeah.
only used the Redstone software. We have just to implement the things we have to implement from some literature review or some other things. But what type of from which manufacturers we get the refrigerant, or how to implement the strategies in real time, we did not do calculation for that. We have only implement in the Redskin software.
I have a question on the PV system. So in the instance of a grid shutdown, how do you deal with powering the building, since your PV system would go down as well?
Okay, so in instance of a grid failure, we would say, so the school is already equipped with a backup system. So we have mentioned in the context, it lies in the, it lies in the boundary of a university already. So the university already have a backup system available. So for that reason, we haven't considered any backup system with our PV systems in our proposed retrofit.
Thank you. And what kind of backup system is already existing?
Well, there are multiple kinds of backup systems that are already available. First of all, there is a great kind of system that is available in our university, which is also powering almost all the buildings in the university. So first backup is over there. The second one is definitely the diesel generators that are available. And in case of grid failure, it's very less often over here, especially in the capital, to have a grid outage.
Thank you.
I believe in your presentation, not in your presentation, but in your materials, you mentioned something called a PDLC window film. Can you?
Yes. Basically, PDLCs are the smart windows. We have already glass windows in our building. They are called PDLC smart films. They are deposited on the already placed windows, and we have also find the cost of their per feet square. This is around 230 to 240 pounds per feet square, and we have also included the cost in the analysis. So basically, this is a film which can be deposited on any window that is already present in the building.
So if I understood what I read,
Yes.
it said that it also had photovoltaic properties. It could generate electricity. Is that correct, or did I misunderstand?
It didn't have a. We cannot get any output from the smart film. Basically, it operates on electricity. We can turn it on or off depending upon the condition.
I understand.
Okay.
Okay, I understand. I just, there was a word in there. It sounded like you were saying that it generated electricity also, and I'm not aware of anything like.
Okay. Okay.
Thank you very much for your presentation. I thought there was a lot of thoughtful consideration. So this is what I ask. How old is this existing building?
It's around this is around 4 years.
It's
4 years old.
4 years old?
Yes.
So
Yes.
what was the mindset that prompted you to think that this would be a candidate for what you're doing versus either a newer, or I'm sorry, a brand new facility, or an even older building or property to affect these same types of changes?
Well, basically, as you can see that this is a new building. So we had other options like old buildings, but when we considered the cost analysis, we have a lot of cost on old buildings, and as you can see that as we know that every building has a certain age. So we choose this building because it was new and it can run like of 4 to 5 decades.
Additionally, new building doesn't really require a lot of structural changes as compared to the older building. So the idea of the integration of technology could easily be achieved in this newer building as compared to the older ones.
Moreover, we wanted it to be a paradigm for, a kind of sample for all the new construction towards a sustainable building design. So that was also one of our thought process while selecting this particular building.
Thank you.
So your design using the chimney effect with that second skin of travertine, that helps you to exhaust heat from that's being absorbed by the travertine. So what happens in winter? Right, because you want to capture the heat, right?
Yeah, in the winter, it simply prevents the indoor heat from coming out. Basically, it doesn't allow the indoor heat to go out in winters. It retains the indoor heat, which results in
The
energy
chimney
efficiency.
effect does?
No, not the chimney effect, but the entire rain cladding system and the polystyrene strip we have given. It also results in the indoor, promotes the thermal comfort of the indoor temperature in winters. Chimney effect is mostly for winter, and so for summers.
So I believe you listed this as a K-12 institution, and I didn't see inside of your design considerations the differences in the learning environments for the different ages of students. Did any of that, your occupant, come into play into your thought process for your design elements?
Yes, of
Yeah,
course, we have considered, yes, on China first. Yes, we have considered design according to the equipment contents. We have considered the lighting, especially lighting for the kindergarten students, for the libraries, and for the libraries and offices. We have incorporated the smart lighting system, and we have calculated the lux of every office and every classroom to make sure that the students are getting, we are getting more efficiency from the students.
Can you tell me more about the community engagement piece and how you interacted to come up with a design?
Yeah, I'll like to answer that. Okay, so coming towards the community engagement, we conducted a pre and post surveys. In the pre-survey, we definitely involve all the stakeholders from the developer of the school to the operator of the school, as well as to the students which were there. All the problems that were identified were based on that survey that we conducted in our initial stage. In the post stage as well, we also conducted a community and market engagement survey and utilized some advanced qualitative research methodology. And as you can see in the current slide that is being displayed, these were the verificances, the main outcome or inference from our analysis.
Additionally, we have designed spaces and we have given a lot of social nodes where people can sit and they can socialize and they can foster community bonds, the students themselves there. But since it is located in a university premises and our university has very strict codes about the functionality, and so we're going to actually add a function that could further promote and bring all of the community of the Nurse University together. So we had a limitation in that aspect, but other than that, we try to cater to that community aspect through giving our social spaces, through designing the social spaces.
So let me ask kind of a little bit of a two-part question. Inside of educational facilities, we often have kitchens and other kind of heat-producing building spaces. Was any consideration given to those types of spaces and how you might have energy recovery, and then also to how that space works within now knowing that this is just a relatively new facility, how did all of those spaces kind of factor into your considerations?
Well, and in current building that we are talking about, the design we presented about NCLS, there isn't any such thing that is available over here. Yes, there is a centralized kind of kitchen that is available, but that is in a totally different building located in some different locality. So that wasn't part of our scope for this particular project.
Can you explain the, you have photovoltaics over that kind of curvy shade structure? Is the photovoltaic just a flat panel above it, or is it curvy?
Well, yes, it is a flat kind of panel over the pavilion, but we are currently developing such panels as well, which can provide us that flexibility with the keeping up with the efficiency of the market available commercial solar PV panels.
Okay,
So
that's
it's
fine.
more-
I just wanted to understand. With the water buoyancy louver system, very interesting. I've never seen something like that before. How is it? Does it have water pumps in it, or is it based on like heat gain or something? I don't understand how. Do you pump water up and then it kind of drains back down and then you pump water up every day, or how does it work?
Okay, so I'm going to explain the working of the water buoyancy system. It's quite interesting and fascinating. Basically, external shading device, it comprises of three parts. That is the outline frame, the drive device, and the floating provided liquid compartment. The frame is simply equipped with sun shading panels that turn upward with the upward force of the floating boards, and it provides the appropriate amount of shade according to different sunshine angles. One end of the drive device is simply located inside the liquid and compartment while the other one is connected to the panel through a link which moves upward with the increasing level of liquid zephyr. And thus, as a result of which the sun shading panel is simply used to force to turn when the sun shielding angle is required to be changed. The liquid compartment then further consists of two links, interlinks, which is the upper and lower chambers, and the liquid is then allowed to flow within the upper and the lower chambers. I can further explain how they work if you want me to, but I don't think we have enough time. But I can explain the further working of the device if you're interested.
Yes, we are at time, unfortunately. I would like to thank National University of Science and Technology once again. Thank you so much for presenting and for answering all those questions.
Thank you. Thanks so much.
Next. Next up, I would like to invite the University of Arizona to come up for their presentation.
خب به خاطر اینکه شاید آقای مشبر
Good morning.
Morning. If we were a little.
Here, put them all right here.
I'll make room.
Maybe one down there.
One down there. Yeah.
Click on my phone. Oh my God.
Did they work off?
That's a good trick. Good trick.
We need to get more time, huh?
Sabotage the other guy.
All right, yes. Serious.
Oh. I'm looking at
All right, looks like we have a full room for this one. University of Arizona, you may now start your presentation. Good luck.
Good morning, jurors. We're the University of Arizona's education team. We're the University of Arizona's education team, and this is the Tawa Ovi Career Technical Education Campus. My name is Nikita.
Christian.
In January of this year, the University of Arizona teams went up to the Hopi Reservation to meet with our client, the Hopi tribe. They had asked us to propose a potential design for a career technical education, or CTE, campus for grades 9 through 12 at their new Tawa Ovi community, which was completely off-grid. There, we met with local community leaders and our clients to get a better understanding for the vision that they had for this project. One such key advisor that has helped us throughout this entire project is Andrew. You might not be able to see him on that photo now, but there he is in the back.
To give context, the Hopi Reservation is located on the Colorado Plateau of the Four Corner region. The reservation is about equidistant from local cities such as Winslow, Flagstaff, and Durango. Our site is located on the north of the reservation, away from major population centers in First, Second, and Third Mesa. The reason for that our client, the Hopi tribal government, chose to build Tawa Ovi outside of clan-owned area. The blue area highlighted is a clan-owned land. These lands are surrounded by historical major population centers that leaders have maintained for centuries. As this land is separate from the tribal government, the site was chosen to be built on the north of the reservation to preserve this culturally significant land.
On the reservation, centuries of forced displacement and disinvestment has left the reservation with few resources. Many on the reservation leave to seek higher education opportunities outside, but then struggle to find homes and jobs when they come back. As you can see from this population pyramid graph, you can see huge gaps in between where the Hopi tribe and the rest of Arizona, where there's huge gaps where working age adults should be. Our goal with the CT campus is to foster a new sense of sovereignty over their future among the Hopi, creating educational opportunities at home.
We're located in a 5B climate. That means that it's going to be predominantly cold and dry. Yes, in Arizona, there are some spaces that are not hot. Continuing from that, we're going to also have our prevailing winds coming from the southwest. They're going to be blowing in at roughly 39 miles per hour. We're also going to have our scarce precipitation. This means that the majority of our rain is coming through our monsoon seasons in the summer. And with our partial monsoons, we're going to have a lot of other days throughout the year where it's going to be sunny, and that's really good for our photovoltaics. For our design goals, we have them split into our climate strategies, our design goals from our Hopi clients, and as well as that, we're going to have our remote off-grid location, which is all being utilized to inform our design decisions for a net positive PHEIS plus sustainable campus.
All right, and this is the current Tawa Ovi site. It is untouched, isolated, and off-grid. The site is only accessible through that main road. Here is the University of Arizona's scope within Tawa Ovi. Highlighted in this light blue color is our site. It is the largest of the sites, and it acts as a central hub connecting the main road to the multifamily and attached housing developments to the east of our campus. However, we envision Tawa Ovi becoming a new city and cultural hub for the Hopi people. As the community develops, our 3 University of Arizona projects will become integrated into a larger master plan.
Within the scope of the site, the campus is broken up into smaller buildings for the CTE campus with a primary focus on agriculture, culinary, veterinary, as well as metal and wood fabrication shops throughout.
With 6 main buildings in total, the program was requested by the client. Highlighted in blue tones, we can see the campus rec, workshop, and central classrooms. On the east of the project, highlighted in orange tones, there is the admin, the success center, and the vet office, which is closest to multifamily and attached housing buildings.
The building's basic form began by organizing the program. Our next goal was to preserve the existing site as much as possible by just allowing the buildings to flow naturally with the landscape while terracing the center courtyard to allow the Hopis to practice their traditional dry farming. And next, we put up wind barriers on the western ends to protect from that prevailing winds. And then finally, solar shaded parking to power the microgrid, as well as clerestories for daylight to enter the buildings.
The materials chosen for this project are commonly found in Hopi vernacular. The use of natural materials such as mass timber, clay-based plaster, and local sandstone help ground the project within its environment.
We partnered with Timber H Systems out of Durango for our prefabricated roof and walls assemblies. They use wood from local Durango forest that had been harmed by mountain pine beetle infestation and would otherwise go to waste. These panels are created into CLT, shipped to Tawa Ovi, where we are able to have local workers and students learn new skills and develop the economy by learning to fabricate these prefabricated modules.
So these prefab panels are built particularly for the climate that we're responding to. The walls hold an R value of 53.82, while the roof panels hold a similar wall assembly. They have a thicker layer of added cellulose, bringing their R value to 71.8. And for our windows, we went with the FIAS certified Alpine Tyrol series windows, and it was important for us to maintain FIAS certification throughout the scope of this project to to achieve that, to lower the overall campus energy consumption. And using these prefabricated panels ensures an airtight envelope with no thermal bridging. And one of our other client goals that we were responding to was flexibility. Primarily with the workshop and classroom spaces, we incorporated a retractable interior wall to allow those spaces to expand or compress to accommodate a wide variety of activities.
Here's an example of a double capacity classroom that has the operable wall open. This allows for a flexible learning opportunity.
So we're FIA 0 certified. How do we get there? Passively, we're going to be having our systems where we have it set up by our air quality monitors, and how those are working is they're opening and closing our windows so that way we can control how much heat is entering there, and we can use the heat stack effect to clear out as much as possible. Continuing from there, we've also done solar analysis. So we've shaped our roof so that way during the summer, no radiant heat goes in, but during the winter, it reaches that back tiled wall, which functions as the thermal mass. That's being put there so that way it can collect all that heat and slowly radiate out throughout the day.
A key part of establishing resiliency in this project was through our water conservation system. In such a dry climate, water was essential to design. And through our terrace farming and roof drainage systems, we were able to collect nearly 150,000 gallons of rainwater annually. In addition, we can reuse 109,000 gallons of gray water to help irrigate our terrace farming and native vegetation on site. When monsoon showers occur, rainwater flows from terrace to terrace, bringing our corn crops to life, and excess rainwater is then routed to the water collection tower. The water collection tower collects and filters gray water and rainwater. The water stored in the tower is used to irrigate the terrace farming and native vegetation on site, while black water is routed to a wastewater treatment facility.
Our building is also designed to work efficiently outside of school hours with a mechanical and electrical system that works by through zones. It works in tandem with passive systems to heat, cool, and light spaces when only occupied. Additionally, we have a BAS that works with the school schedule to make sure that heating and cooling is routed effectively.
Effective air control is necessary in an environment prone to harsh, dusty prevailing winds. That's why we implemented an ARV system, as well as monitoring windows which work in unison to bring fresh air into the spaces while exhausting stale air, removing harmful pollutants in the classroom spaces. This better helps, and fresh air has been shown to improve attentiveness and cognition among students.
Considering our client goal for cultural continuation, the campus was designed with points of interest for the community to come along and interact with. The campus is programmed to provide for community needs, to help develop the economy, to establish cultural amenities, and create recreational areas.
One such community engagement tool is the workshop, where it's a focal point of this project, as it aims to empower the Hopi through hands-on learning. Participants can build, maintain, and engage in the construction process, fostering the skills and confidence needed to shape their own future.
Our Hopi clients expressed a need for an architectural language that reflects the Hopi traditional way of designing. We created a massing that reflects the Hopi vernacular and creates a true Hopi identity. On the interior, we also used baffles in the ceiling to minimize negative acoustics while also reflecting on and echoing a traditional Hopi ceiling. Outside in the terraces, we've created space for the Hopi to continue their long-standing tradition of dry farming, creating spaces for them to use their century-old techniques with their resilient crops.
To make the campus as efficient as possible, we utilize daylighting models to analyze lighting conditions inside the building. And for our classrooms, we primarily utilize clerestory windows. They leave a nice, well-lit desktop condition. And in spaces like the dining hall and study hall, we use eye-level windows to provide for slightly dimmer spaces, as well as views outward per Hopi request.
The Success Center is a hub of productivity and social interactions. We try to balance the cultural preference of having dim lighting while still being effective at tasks, thus creating a welcome environment for the Hopi. Bright day lighting was also an important for the gymnasium, a vibrant center of sporting activities such as tennis and volleyball, and most importantly, basketball, which is historically relevant to the Hopi.
The clerestories also aid us in energy efficiency. As you can see, they bring in more heat gain than heat loss in winter months, as verified by WUFI. With that, along with our highly insulative wall and roof panels, we're able to bring in our UI down to -11. With off-grid in mind, we needed excess energy for peak loads during winter months such as December and January. With our photovoltaics, we're able to generate nearly 280,000 kilowatts under ideal conditions. This means that we can offset even the most intensive loads during winter months. In addition, keep going.
For our mechanical systems, we have a hydronic radiant system, not radiation. That one is there so that way we can effectively heat and cool the space. Outside, the dew point never goes above 60 degrees Fahrenheit, so we don't have to worry about condensation building up on the grounds. Besides that, we also have fan coil units in there to work on our occupancy shifts. And during our occupancy times, we have zoned all of our spaces so that way it can be as efficient as possible.
In addition to our array of photovoltaic systems, we have coordinated with Tawaovi community to work with an islanded DC microgrid. Using Block Energy, a commercially available product that we have partnered with, Excess energy is gonna be generated and stored at the same building. And excess energy is gonna be used to offset throughout the community, since energy demand at the campus peak different than housing developments. The stored energy can be redistributed where needed, keeping the community powered throughout the days and winter months and overcast days. By sharing energy, we assure our grid sustainability.
Compared to typical construction, our use of low carbon materials as well as local ones that are found locally, we're able to bring down our embodied carbon significantly. We used one-click LCA to find that our building proudly got a score of B despite its remote site.
Thanks to the reduced cost of domestically sourced materials, we estimate that the CTE campus will cost approximately $282 per square foot in comparison to a typical construction cost of $300 per square foot for our site.
We'd like to thank our advisors and everyone who's helped us today, and thank you for your time.
Great job, University of Arizona. Very well thought out presentation. Let's open it up for question and answers. I'll hand it over to the jurors.
I'll hit one. You've introduced quite a few relatively passive types of systems into this, and I applaud you on that. But one of the curiosities that I had was with regard to the water storage, the sort of on-site cistern. Can one of you share with me a little bit how you size that and what the anticipation is for distribution, that kind of thing? I mean, it's there, but does it work?
Yeah, so the idea there was we were able to get an estimate on how much our roof drainage system and terrace farming would be allowing us to collect in water, and then we just sized that accordingly. As far as how that works, we know that we have to install like a filtration system that's going to be adjacent to the water collection tower. We haven't really gotten into exactly how that tandem works with like the filtration of gray water and then the water collection tower, but it looks like Nikita wants to say more.
Yeah, I just wanted to add real quick that is something that we've really been wanting to consider. We've done the calculations to see the potential, how much water we can receive, but we haven't been able to work with anyone just yet about realistically how big that cistern and water tower would be to accommodate all that water that we're picking up. But we would use it primarily just for irrigation of the systems because it is such a dry climate out there.
Thank you.
2 questions. First one is your site, you said, is off to the side of the main part of the Hopi community. And is there actually a grid there? Is there water there? Is there sewer there? Or is everything kind of trying to live off grid? And then the second question is for the off-grid PV electrical system, I didn't see anything. Did you look at like month by month what you're generating and what you're using and balance them?
Okay, so for the site location, it's located on the north of the reservation as a totally new construction with the consideration of like the tribal land. Most of the tribal land, local leaders want to preserve it and keep that boundaries of the history of
No,
the land.
I just need to know.
Yeah,
Is there something to connect to, or is it like?
No, it's
totally-
totally new. It's totally off the grid.
So
Yeah.
are you intending to connect it back to some central system, or is all the water, everything independent? And
The
you
whole-
have to collect
yeah.
and live off your own water and energy?
So the site is incredibly remote. We have access to some local water wells, but they're not like, they're not US centric. We can't even connect to the power grid out there. It all has to be completely remote. Something that I forgot to mention on the photovoltaic side is we did run those calculations on if we'd be able to power each month, and we found that even during the highest peak months, our photovoltaics are basing the idea that the photovoltaics will only generate 40 to 60% of max capacity in winter months, we were able to know that we are offsetting loads with how much our PV are generating. And in addition to that, we do have the microgrid system working in cases where there's just too much peak load for this campus. Other buildings and excess stored energy can offset any loads that we have here.
I thought you were independent.
So to summarize everything, just so you're not confused, the whole entire system is off grid. It doesn't connect to anything. There's nothing there with the exception of a sewer line that currently exists, completely separate from anything else. It just currently exists and plans to be implemented into our project.
Okay, so back to on the energy side.
Yeah, I understand the confusion. So we have a TAWA-OV microgrid. It's a DC island microgrid system that works only purely within a TAWA-OV. So we have a battery farm, we have photovoltaics from the campus, from other buildings. That all powers
Are there any other buildings than what we saw? It sounds like you've got a whole other community, but I only saw the.
Two phases. This is phase one, which is what we're all building. And that just includes our other multifamily attached housings. And then in the future, around 2040, we're expecting the community to build around this, in which case we'll have additional block energy like central hubs.
So what are you gonna do in the meantime?
Well, we have a central photovoltaic farm. We have our building is net positive. We have other community buildings, the attached housing and the multifamily housing, which are also pushing.
They're not gonna be built yet, are they?
No, this is all part of the scope. This is all part of the scope
Oh,
altogether.
okay. Got it.
If I understand it, you're actually just adding to the TAWA-OV microgrid. As you
Yes.
build and develop, you'll be supplementing it because the
So-
microgrids are pods, basically.
Exactly.
So the housing and everything else is already gonna be there?
Yes, it's being built along with the campus.
Can you go back a few slides? Because I want to talk to you a little bit more about your mechanical systems. Go back, no, a few more, one more. Okay, yeah, that's what I wanted to see. Wanted to see a little bit more about your design degree days, what your design temperature ranges that you used while you were modeling, kind of your overall tonnage. And then pairing that back architecturally with your programming, because you're in separate buildings and it appears to not be taking advantage of the diversity of mixing the space types, the heat loads, all of those elements. So kind of an overall question was, how did you use this information, kind of your quantifiable climate information, design degree days, temperature operations and all of that, and your programming? How did those two talk together? Because I'm wondering if you have gone as far as you should have gone with deficiencies in some, and you might have kind of operational and occupant comfort issues in other buildings because of the decisions you made during the process.
So thank you for asking. Just a little bit of a lot to answer for that one right
There
there.
is a lot, yeah.
So I guess the best thing to do is to like walk you through the design and the thought process going along so it can help you understand the idea. So when we first started this, we talked to our clients about what they wanted, and they were specifically asking for these dark, dim spaces. And then they also wanted to make sure that there was some degree of flexibility, but we also wanted to give them a little bit of privacy and separation. So that's how we came up with the initial design for it. After doing that, we started to study all of our WUFI passive strategies that they came up with. And we were noticing that we primarily needed to heat the building because there's very few actual warm days there. So considering that, we thought of the best ways to do this, and we were figuring out that we need to block against the wind, and that we also need to make sure that we're applying as many passive and active heating strategies as possible. So in order to do that part right there, we wanted to try to keep true to Hopi traditional ways of living and their styles, at the same time implementing those passive strategies into the project, which is why we primarily focused on the roofs, because they're very complex out there, and usually all those come together to make this very dynamic architectural piece. So we wanted to raise them a little bit at clear story so that way we can get as much passive light and therefore passive heating into the building, while also trying to keep the spaces as dim as possible, like they asked.
What was your glazing, by the way?
Glazing.
Window glazing?
It was the Alpine Tyrrell series windows. It has a U value of 0.144.
Thank you.
Let me build on that real quickly. Clearstray seems to be a big element of what you're doing. I mean, it responds to some cultural needs. It obviously responds to an aesthetic need. Was there consideration for individual sizing for clearstrays in each one of the program spaces? And was there any consideration of active control of those clearstrays?
Yes, and yes.
Okay. I just didn't see that documentation,
Yeah.
but I'm gonna trust you.
Yeah, it's no problem. We have taken those into consideration. If we go back to the daylight analysis, which I think is after this, if I'm correct, or is it before? Before, thank you. Sorry, I just wanted you to be able to visually see it. So what we did is we used this primarily to study how light was currently working in the building, and then we adjusted it. So there are spaces like the classrooms where we want like more natural soft light, as well as the library. So that way you can have desks that are lit up and you can have these spaces that are very comfortable. But then you have spaces that are more like community, where like the education center, where you want to have these nice views in these dim spaces that they asked for. So we've kind of been balancing what the aesthetic and the traditional needs that they want with realistically how those spaces will function and what kind of lighting conditions you'd want in those. Does that answer your question?
It does, it does. Were the models themselves used for, pragmatic study? Did you actually do casting analysis through them or anything? Or are they just
So the model is kind of like the final step we took, because we did 3D models instead of physical models for these.
Sure.
So we can analyze the daylighting and everything. And we initially wanted to build a couple of test models, but since we literally started the project in January, we've been very constrained on time. So we've been primarily focusing instead on our digital models and then just building physical so you can understand the idea in person.
So this is 90 days of work I'm looking at.
Yes.
Okay, thank you.
So a CTE space, so there could be considerations there for what is the CTE program, because that impacts kind of the mechanical systems, ventilation requirements and air changes that are necessary. Talk to me a little bit about how you dug in there and what it is.
So the CTE space is our main classroom building. So these are meant to be flexible spaces used for a variety of different needs. They're general classroom spaces, each zoned separately, so that when, for example, it's after school hours, there is a after school program being done, we can make sure that that space is getting the full heating, lighting requirements that it needs, while the other spaces are off.
We're talking book-based learning. We're not talking about, auto mechanics or anything, and I threw that one out as a crazy wild one, but we're talking about book-based learning.
Well, so that's the CTE space.
Okay.
Now the building is separated into 6 different spaces for other CTE, more like hard. Like, for example, the veterinary is a space that's specifically done for students to understand veterinary, to create education opportunities there. And that one has a different system of air change. It's more, it's obviously more than the classroom spaces, but it's also dimmer because it requires less. We didn't put in so much consideration into making sure that it's a well-lit, daylighting lit space.
Metal lab.
And then the metal lab is actually fully non-conditioned, because we're able to make sure that that space is used only when it by itself, it functions off primary passive strategies, entirely off of passive strategies, which keeps it comfortable for most parts of the year.
All right. We are at the end of our Q&A session. So I want to thank the University of Arizona once again. Great job adding more detail in your answers. Thank you.
Thank you. Hello, everybody. Hello to the juries. We are the Green Sparrow team from Tehran University of Arts. We have come together to address social problems in a selected urban area. The four main objectives of our team in designing the Green Sparrow School are reviving the social fabric, decreasing carbon emissions, increasing economic productivity, and resilience. To achieve our design goals, we utilized various software tools. Site selection was one of the most important steps in our team's design process. Accordingly, the distressed social, economic, and cultural fabric of the Shush neighborhood in Tehran was chosen as the design context. In addition to social and economic considerations, climatic conditions, vegetation coverage, and natural hazards, such as earthquakes, were taken into account. As a starting point for the design process, a detailed climatic analysis of the site was conducted. Furthermore, interviews with inhabitants relieved the needs of the neighborhood. One of the key objectives of designing a green school, which had a notable influence on architectural and educational aspects, was the revitalization of Iranian culture and art. To revive past architecture, the first step in architectural design was to divide the design into two parts: new construction and redesigning the existing buildings. It was decided to design a school as a neighborhood center. The new construction was designed modularly, incorporating elements such as Chahar Taghi, Avans, and central courtyards. By redesigning existing buildings and revitalizing them for the new uses, the design team preserved about 68% of the existing buildings. The design of interior spaces in proportion to the overall school design was inspired by Iranian architecture and culture. I think I don't have access to slides. The design of interior spaces in proportion to the overall school design was inspired by Iranian architecture and culture. Inspired by Chahar Taghi form and using modular design, and design team utilized second-hand scaffold pipes as the primary structure material. The life cycle of second-hand steel pipes with very low carbon consumption over their lifespan, simple construction, the free form of architecture aligned with its cost effectiveness compared to alternative methods was emphasized. To construct the mentioned modules, firstly by constructing one of the four module sections, other sections are easily constructed due to symmetry, and the module was quickly assembled. To enhance earthquake resilience, the structural engineering team has proposed a space frame system. One module was fully analyzed in SAP software. On the other hand, a structural module has a very high degree of static indeterminacy, and the smallest repeating components that make up the structural module have geometric stability. Integrated simulation of renewable energy production systems and transient HVAC systems was carried in Transys software. To provide cooling, heating, and domestic hot water load, compact air-cooled chillers, steel boilers, and their complementary equipment were used. We use fire tube boilers for two reasons. First, heat pumps are not common in our country and are not produced domestically. Therefore, we are forced to buy foreign samples. Second, a large part of electricity production in our country relies on gas. Air supply for cooling and heating through suitable ducts required careful consideration. The design team evenly distributed airflow throughout the space by considering two air zones and routing ducts through the structure. Renewable energy production on the building site was carried out using BIPVC, PV, air-based GHX, and water-based GHX systems. Ensuring fire safety and greywater recycling in the building were meticulously addressed, similar to other utility sections. Detailed design aspects are presented in cross-section to better understand the installation of utility systems and renewable energy production. To achieve the goal of carbon reduction, the design team used free innovative materials, second-hand steel pipes, structures as a structural elements, Vitasour as thermal insulation, and algae as the final coating. In addition to its pressure resistance of about 3 megapascals, algae also exhibit a hardness equivalent to laminate hardness, making it easily usable as flooring and wall covering. Construction of the new building and retrofitting of the existing building was carried out using dry connections and eliminating thermal bridges in all sections. Detailed execution of the new building using dry connections effectively eliminated thermal bridges in every section. For redesigning the existing buildings, 68% of the structure were preserved, and with the addition of thermal insulation, new columns, and roofs, the existing building was structurally reinforced. The construction details of the building were analyzed using TherM software. The thermal specifications of the existing and new building envelopes were calculated and compared with Iranian National Building Code regulations.
In the first step, the energy consumption of existing building was 610 kilowatt-hour per square meter. And after designing the new building and retrofitting the existing part, the energy consumption reached 167 kilowatt-hour per square meter. Finally, with on-site energy production, the final energy consumption of Green Sprout School reached -11 kilowatt-hour per square meter. The 4 renewable energy production systems on the entire site have a capacity of 18 kilowatt-hour per square meter. Considering that the large portion of primary fuel in power plants around Tehran is natural gas. The engineering team decided to directly use gas for the boilers to avoid energy loss in converting gas to electricity at the power plant. It is worth mentioning that the selected boilers have an efficiency of 19%. One of the most important effects of the energy production and consumption is carbon emission, among which the share of carbon emission from renewable energy generating equipment is less than other sections. Rainwater collected on the building roof is directed to the courtyard by gutters. Then transported to an underground reservoir through subsurface courtyard pipes, and from there it will be purified toward the pump room. It is worth mentioning that all purified water except for rainwater, which is used for potable, is used for purposes such as watering plants and filling flash tank. The Green Sprout School building's connection to its surrounding energy, water, and waste networks includes buying and selling electricity, selling heat energy in the form of the hot water, selling purified rainwater to grid, buying the tap water, and delivering segregated waste to the waste management network. It is worth mentioning that produced water, hot water, is transported through pipes to some buildings such as the mosque and a sports club near the school. Environmental education for students to preserve the environment and reduce carbon emissions includes reusing workshop fabric scraps as urban furniture and exteriors, as well as wheat collectivation for green mycelium material. Also, managing materials resulting from the demolition of existing buildings on the site, bricks from the were used as a part of the new building's facade. Using LCA one-click software, emissions resulting from material consumption, transportation, repair and replacement, demolition, and energy consumption in both the new and existing building section were evaluated. The carbon footprint of the new and retrofitted buildings is estimated to be 294 kilograms CO2 per square meter and 190 kilograms CO2 per square meter respectively. By selecting materials such as second-hand steel pipes as a structure, circularity in the building is estimated at 61%, and the old building, it is 65%.
The design team ensures the health of students and the staff in 4 areas, providing fresh air, using low emission materials, using certified wood materials, and controlling various pollutant entry into the building. To improve the quality of education and teamwork training, our team plans to design flexible furniture at the highest level to achieve the goals mentioned earlier. To promote health both inside and outside the building, our design team has increased respiratory quality by planting vegetation. By considering appropriate mass in building walls and using stone wool as sound absorbers in walls, sound transmission in the building is controlled to a satisfactory level. Another important acoustic parameter in a space was the reverberation time, which was controlled to an acceptable level by simulating its value. For example, reverberation for a classroom is 0.9 seconds in 500 Hertz. The design team simulated lighting conditions using Climate Studio software to regulate the quality of light and use of natural light and achieve a 3-star rating according to LEED standards. Additionally, to distribute artificial lights uniformly in the classrooms and offices and provide illumination levels between 400 to 500 lux on the surface of tables, the conditions were analyzed by Dialux software. To improve the economic conditions of the school students and neighborhood residents, the design team explored income-generating opportunities by renting commercial spaces to residents at prices lower than the market rate. This would enable students to receive discounts for purchasing educational supplies from school-owned shops using student bank cards, allow students to sell their artistic products and earn income, and provide communal spaces such as amphitheaters, libraries, as well as exhibition booths to the neighborhood residents. By selecting appropriate construction methods, suitable structural system, and precise scheduling, the design team was able to reduce the construction period of the school by 40% compared to a typical school. The construction cost of the new green building is estimated at $283.37 per square meter. This figure is $74 less than conventional schools in Tehran. To better understand the economic conditions, the design team calculated the economic conditions in the risk analysis. It was determined after analysis that the construction cost was the school would be recovered over 12 years. By revitalizing commercial spaces, providing communal spaces for the neighborhood, organizing temporary exhibitions, and setting up sales booths for the neighborhood residents, the school will play an important role in connecting with its community and acting as a neighborhood hub. To strengthen the school's connection with the neighborhood, the Green Sparrow School adopted a flexible scheduling program. And here is how does the school interact with the neighborhood. Secure connection with the park, crime reduction, improve public culture, encourage nightlife, longer working hours after school time, encouragements to read books, make the place suitable for women and families, teach skills to girls students, and become due to its modular nature, the school will be easily expandable in the future. The resilience of Green Sprout School building is such that during crises and epidemics, it can serve as a haven for neighborhood residents in such situations. With rapid deployment, it can easily provide services to people seeking shelter. Here are our project highlights. I'd like to thank our advisors and team. Thanks for your attention.
Thank you, Tehran University. Very well presented. Let's open it up for question and answers. Over to the jurors.
I'd like to start with your ground heat exchanger, please. Could you just tell me a little bit more about why you chose a horizontal loop field where it's actually located on the site? If you explored having the correct amount of room and all of the modeling associated with balancing it. And then finally on that, did you look into the thermal conductivity of the geology of the site? And I know that there's a bunch of questions there, but just maybe hit a couple of those that you think are the most interesting in your exploration.
Actually, could you mind repeating your question? I'm not sure they heard it.
Sure. Okay, so I want to talk about the ground loop heat exchanger. And I want to understand a few more of the details. I'm going to ask you or give you an option to explore some of them, but you don't have to talk on them all. One, why did you choose horizontal? Where is it located on the site? Did you explore the thermal conductivity of the geology? And is it fully balanced in order to kind of account for all of the heating load?
Hello, juries. Hello, Solar.
Could you be a little louder? We can't hear you very clearly.
Can you hear me?
A little muffled, but just try speaking into the microphone directly. But go ahead.
Hello, juries. Hello, Solar Decathlon. We used air-based and water-based ground heat exchanger because of preheating or pre-cooling the air for supply heating and cooling the rooms, such as classes and shops and workshops and other places. The soil conductivity in Tehran is about 0.57 watt per meter Celsius, and we use the ground air-based heat exchanger to preheat or pre-cool the air and send it to the directly to the AHU systems. If the air temperature then pass through the airs between 18 to 25, the air directly to the AHU and sent to the condition zone. But if the air temperature is below 18 or above the 25, the air first sent to the AHU for more cooling or more heating. But the water-based heat exchanger used for storing thermal energy in the airs. For example, PIPVT systems generate hot water and it will store in the airs in 1 month. In other months, the tap water first pass through these pipes and preheat, and then for certain design temperature sent to the boiler and used for potable use and drinking use and other uses. These two types of heat exchanger were used in our
We
Maybe
lost you.
let's move to another
project
question since he froze.
and
right.
put
right.
in the site better. Excuse me, I didn't understand what you said.
So your screen's freezing up a little. Maybe we'll move on to another question.
Oh, yes.
I apologize. Maybe you did describe this, but I didn't capture it. What is the interaction between your PV, and if there's some calculations to substantiate that, and the dependability of the grid in this part of the area? And I think it's specifically maybe addressed in 5.5.
Excuse me, your voice.
Were you able to hear the question?
Yes. PV is only used for generating electricity. So we used control charge and batteries to store this electricity. But when the battery is full and the school didn't need any electricity energy, the produced electricity is directly sent to the grid and sent to the grid and so on.
Understood.
There was mention in your narrative something about algae panels. Can you talk about that a little bit?
Yes, algae panel made by algae collect from the river or dam or something like that, and bring to our site and shape it and form it, and it will dry because of the solar radiation. The partners, according to SureD test, is about 60, something like that, held. And compressive strength of the algae is about 3 MPa. And also tensile strength of the material is about 7 MPa. And something like
Your screen seems to be frozen.
that, use this material for this material is free from things. Excuse me, produce this material. We make this material. It's not just
Is it on the screen?
visual. Yes, yes. These types can, and this one, and also this one. It can form very easily, and you can use by dry connection on the floor or on the wall.
And the algae panels are only used to a certain level, and then it moved to spun rock wool insulation, and then I don't know what was happening above that.
We didn't use the algae panel as a thermal insulation. We just use this as a covering, floor or facade. For thermal insulation, we use mycelium waste, which first gathering from the farms of wheat and send it to our site, and then make it mycelium and dry it by using microwave or something like that. And then we assemble these types of insulation to drywall or flooring or something like that.
I might have missed it, but you talked about the water collection and storage system. Can you describe the plumbing system of your building?
Yes, we gathering the water, rainwater from the roof or outside under the earth. Actually, the earth act as a drainage and capture the dust of the rainwater, and then it's stored in the reservoir, stored, we bury it in the earth in the site of their school, and then for using a pump the gathered water to the purified system. When the school doesn't need the water, this purified water sent to the neighborhoods, and the neighborhoods can use this type of water. Another water we gathered is the gray water. The gray
Your screen is frozen again.
can you hear me?
We can hear you now, but we lost you there for a few seconds.
Yes, yes. The gray water first gathered in the main mechanical room and purified and will used for irrigation and flash tanks, toilet flash tanks. Another water we gathered is condensed water from AHU systems. We use this type of water for filling flash tanks and something like that.
I think we have time for one more question from the jurors, if there's any.
Thank you so much.
One more? Okay. Though there was a commitment to using what you described as Shahartaki design and construction for this project. The arched forms, they seem to take up a lot of space, but then they also offer the opportunity to increase insulation, route systems, etc. Was there other thoughts of a simplified system without so much small parts to more quickly achieve these space goals?
In our country, we don't have carbonless material like OSB woods and something like that. The concrete system and metal systems have a lot of carbon emission. So we want to solve this problem by using second-hand scaffold system in form of char topping. These types of forms, because of special characteristics in form of curves that respect of envelope to something volume of the shape, reduce the thermal conductivity between the inside and outside. There is no solution for this because the other types of material we use have a lot of carbon emission. Another point of this answer is that when we use curve forms as in a structural, the structural system is more light than when we use the slab systems. Another point is that we use these curve forms as a part of energy systems by assemble BIPVT systems on the roofs and on the curves, and also we regenerate or revive our ancient architectural forms that we lost this characteristic during years. Something like that.
All right. Thank you so much, University of Tehran. Great job. Thank you so much for presenting virtually.
Excellent job.
Thank you so much.
Thank you so much.
Thank you so much.
Next up, we have University of Illinois, Urbana-Champaign. Can I request all the presenters to please come up front?
Just a heads up, as you speak, the microphone is there, so you either need to share or walk over.
All right, where's the remote to change slides? And also there's a camera right there in case you might wanna try not to block it.
Oh, maybe. It only blocks out me and David, so.
That's the one group, it's like, all you can see is got it back.
You wonder how much of this will wind up on social network at some point. And the caption reads. Well, boom, was attacked.
Does this work?
But you don't have to lean in. You're good.
Are you sure?
Yeah.
Okay.
All right, UIUC, you may now start your presentation.
Good morning. We're Illinois Solar Decathlon, and we're excited to present Ideals, our vision for the future of education in Chicago. Now, here's a brief overview of our team members, presenters, faculty advisors, and industry partners who all partook in the making of this project. Our site is located in the northwest corner of the University of Illinois at Chicago, who is, of course, our main project partner. The site is uniquely accessible through all modes of public and private transportation from Chicago's west and south sides. We show very moderate ETAs from various locations in the inner city, which just adds to the site's accessibility.
The site itself is a massive unshaded parking lot owned by UIC, and it's slated for educational development in their 2024 master plan. It's remarkably underutilized and contributes significant harmful heat island effects to the surrounding community. Ideals seeks to establish an ultra-sustainable model for schools and is catered toward Chicago's most underprivileged populations, whose relationship with the Chicago public school system has been marred with a legacy of systemic discrimination and lack of opportunity. In order to enable this form of social and environmental justice, Ideals aims to provide an early educational intervention to its K-8 students. It aims to rekindle trust between the CPS system and Chicago's most vulnerable communities, who principally reside on Chicago's west and south sides. And additionally, it addresses a legacy of displacement that the construction of UIC's Circle campus unfortunately bears.
The main climate characteristics that Ideals is catered to are Climate Zone 5A's polarized seasons, high humidity, and high precipitation. Though we're outside the FEMA 500-year flood hazard zone, the building also accounts for extreme natural hazard events that are occurring in Chicago, particularly tornadoes. Our design goals are tailored towards enabling forward-looking pedagogical methods in extremely healthy and equitable learning environments. We see Ideals as a learning asset both in form and function, which is why our cutting-edge design strategies and technologies are made extremely and intentionally visible, as well as coherent to all of its occupants.
We align our massing to be suitable for passive building performance. By doing so, we place the classrooms on the outer perimeter of our building, which are then anchored by 3 central courtyards, all maximizing natural daylight. In this, we keep a heat loss factor of 1.9 and a surface to volume ratio of 1.2, greatly reducing the thermal loads. Our site has a 616% increase in greenscape, alleviating the heat island effect and promoting healthy and resilient spaces. At the entrance, students are greeted with a floor-to-ceiling atrium, which highlights some of Ideal's most innovative designs. From our solar tube skylights to exposed mass timber and our internal vegetation, which all promote biophilic design, to our internal architectural stair, which centers as a central space for outside learning. The main welcome screen, supported by the building's BMS system, also allows teachers and students to track the building's energy performance year-round. In collaboration with UIC, Ideals establishes spaces that lend themselves to new cutting-edge learning methods through creating flexible and innovative learning spaces. Our Learning Commons highlights unique forms that encourage movement and openness. As for many of our spaces, we design for LEED and WELL standards, such as ways to optimize data lighting and acoustical performance. Our Innovation Lab is another high-tech space showcasing and integrating the most recent learning methods to introduce students to technical projects with a sustainability-centered curriculum.
The courtyard begins to highlight Ideal's commitment to nature and place without compromising on building performance. We use skylights that are operable and electrochromic, as well as being triple glazed with a low-E coating and a krypton gas fill. We use windows with warm edge spacers to minimize the heat loss factor and also to allow for ample sunlight and natural ventilation throughout the building. We have 2 courtyards that create internal spaces that are going to be beautiful and able to use access year around with greenery that supports the natural sites and the internal air quality. The new landscaping also features a greenhouse and a native plant garden, along with an active playground and paths that connect the whole space. This allows for outdoor education as well as creating more resilience on the site. The vertical fin shading that we incorporated on the north and west facades plays an aesthetic role to interact with UIC's role as a brutalist legacy along the campus. The vertical pattern emerges as a constant motif throughout our site. Similar to other contemporary buildings, we create an homage yet a clear break and not acknowledging the past, but addressing what we must overcome in order for developing a more sustainable and equitable future for students. The kinetic shading is made of recycled aluminum and offers Ideals its main exterior identity. It also provides an adaptive afternoon shading, which is really necessary because we have an extreme cooling demand that we want to reduce throughout the year. We also use a double skin facade along the south face, which is a really well-performing element of our design. This highlights through the therm and woofy models, our thermal, moisture, and humidity performance, which is all crucial to our 5A climate conditions.
To validate this, we took the ExoStrap and ran Autodesk CFD simulations on the double skin facade, which showed the workings of the stack effect, massively helping in the thermal regulation and natural ventilation of the building.
The cafeteria is not only a comfortable, vibrant space for healthy nourishment and mindful waste management, but also a site for renewable tech education, as the algae facade and the kinetic floor tiles are shown. Together, they annually contribute to around 2 kBTU per square feet. Ideals also utilizes a triple glazed PV windows with a PV silicon crystalline layer between 2 layers of gas, alongside low E coating and a noble gas infill. With a 24% average window to wall ratio, the distribution of windows along each facade is optimized to maximize production without compromising fenestration. With 16% efficiency, PV windows impressively contribute to 6.4 kBTU per square feet yearly, with the distribution across each month and each facade as shown. Ideals' east-west orientation and flat roof make it optimal for roof-mounted PV performance. Using 650 south-facing first solar thin film cadmium telluride arrays at 19% efficiency and 34 degrees optimal full tilt, alongside 3 Schneider electric mode inverters with 98% efficiency, PV roof arrays contribute to around 11 kBTU per square feet to Ideal's annual production.
Our Purple Roof system achieves 100% stormwater management on site by providing rainwater detention and retention superior to traditional green roof systems. It also enhances the efficiency of our PV panels through its thermal regulation capabilities. And with an R70 rating, the extra moisture and vapor layers preserve optimal performance. Ideals aims to provide 100% irrigation supply through recycled rainwater, gray water, and black water, while also employing a dual wastewater heat recovery system, which satisfies 100% of the building's hot water demand. 2 separate paths are created for the gray water and black water, ensuring sanitary delivery to their respective Piranha wastewater heat recovery systems. And then they both undergo proper filtration and distribution into our drip line irrigation network. 30% of the gray water is recycled back into our black water channels, while still recycling enough gray water to satisfy 100% of the building's irrigation demands. Integrated with our Piranha system is our geothermal system, sized to manage 100% of our heating and cooling loads for the building. In collaboration with Professor Andrew Stumpf, developer of the GLHE Pro software, we were able to utilize the software as well as market analysis data in order to determine that the Climate Master heat pump in a 4x5 configuration of 20 boreholes with a 440-foot depth was optimal in both cost and function.
Integrated with the geothermal system and the Piranha system, and to increase efficiency even further, a combination of the VRF and DOAS units was utilized for ventilation and HVAC solutions to provide efficient, personalized thermal comfort regulation and optimum ventilation throughout the entire space. Combined with that, and to add to that, we install occupancy, thermal, and indoor air quality sensors utilizing LiDAR technology, all connecting to our central BMS unit. This helps regulate and optimize the air quality essential to a healthy learning environment. A demonstration of the layout of the ventilation and the various indoor local units shows the utility of the VRF unit in being tailorable to each specific space. This helps optimize between the load management and the initial cost. The full circuit logic of our HVAC system and all its components are designed to be complementary to one another, as each system improves the efficiency of the other. For example, the Piranha system helps regulate the fluid temperature within the geothermal system, which thus helps improve the geothermal system's efficiency and operation. This theme of integrating different systems within each other to maximize between all systems efficiency helps improve the entire system's efficiency operations. We also provide 100% fresh air and size our ducts generously to provide high ACH values in compliance with ASHE 62.1 CFM calculations requirements, increasing the space resilience against high-risk events such as COVID-19. Finally, assessing the building's EUI is projected to have a negative net annual EUI of 3.4 kBTU per square foot, which totals to around 580,000 kBTU in excess energy per year.
Ideals pioneers peer-to-peer energy trading with blockchain technology, enabling prosumers to sell excess energy to neighboring buildings through automated smart contracts and discounted prices, enhancing microgrid economic viability. Our AI software by TM Beer and Associates dynamically adjusts HVAC, lighting, and equipment based on occupancy patterns, weather forecasts, and energy usage data. With up to 90% accuracy in real-time consumption forecasting, it optimizes energy usage and storage, reducing peak demand charges and enhancing energy independence. We also integrate 12-meter electric buses featuring static wireless charging, 220 kilowatt electric motors, and regenerative braking for maximum efficiency and range, as demonstrated in the microgrid. In worst-case scenarios, during grid disruptions, our 1,200 kilowatt lithium iron phosphate battery with an 83% load coverage factor sustains operations for 8 hours, ensuring uninterrupted service. The decentralized microgrid, empowered by the AI system, dynamically prioritizes peak shaving and frequency regulation, reducing reliance on the grid.
As shown in our SDA analysis, Ideals achieves an impressive daylight infiltration. We used Relux CAD to model each of our core spaces, where we integrated ambient lighting sensors as well as daylighting sensors. The spaces are lit either using solely artificial lighting or a combination of artificial lighting and daylighting, creating for prime-tuned, suitable, comfortable lighting levels at all times. Alongside our shading system, we managed to mitigate glare in all the places, creating soothing lighting levels at all times and with a peak efficiency.
The structural design of Ideals focuses on economy, functionality, and minimizing material waste, as well as the carbon costs. A 9-inch concrete raft foundation is designed using the site soil data, which was obtained, and the lateral and gravitational systems are designed using locally sourced southern pine wood. The glulam post and beam framing, as well as the CLT panels, ensure resilience against extreme weather events, as well as optimum serviceability. The live load diagrams for each floor are demonstrated as follows, and they're all in accordance with the International Building Code of 2021. And with that, the SAP 2000 model that shows the controlling load cases shows vertical and lateral deflections less than 1.5 inches, which is remarkable serviceability. For us, we wanted to prioritize this space being a safe haven for community members during extreme hazard risk events, and we have thoroughly examined its capability to do so through our structural design.
Ideal's conscious utilization of heavily recycled and recyclable materials reduces its cradle-to-grave carbon emissions cost to 137 kilograms of CO2 emitted per meter squared, which is a testament to its resilience. Moreover, a maintenance plan developed alongside UIC's Planning, Sustainability, and Project Management team, who already have extensive experience maintaining geothermal, PV, and advanced renewable systems on campus, will ensure enhanced energy efficiency and performance across a longer lifespan.
Our team developed an Ideals application, recently approved by the App Store and going live tonight, which aims to cement the building's identity as a sustainability lab. It is integral to the school's security system and also allows users to access schedules, events, receive communiques, and importantly, monitor the building's energy performance and delve further into understanding the renewable systems that maintain net zero operability, making it a vital tool for sustainable education within Ideals.
Ideals has a forecasted cost of around $81 million, broken down as follows. From conversations with representatives of CPS and some research, a proposed financing scheme that's heavily reliant on tax increment financing is shown as displayed.
Now, a proper analysis of long-term energy cost savings is crucial to grasping the real economic utility of the project. Though we estimate that upfront, the project is about $16 million more than would be typical, the lack of energy utility bills for a similarly sized building and a 3.25% forecasted inflation rate says that this building would save $300 million over its 100-year lifespan. Well, actually, it's closer to around $210 million when some maintenance and operability costs are taken into account, escalating with inflation and with increasing complexity over time. However, the microgrid pays back for itself in about 40 years, which means that profits after that point purely escalate the entire project's profitability. And that $16 million upfront is covered in 36 years, whereas the total cost of the project is paid back in 76. This doesn't also quantify the real social, environmental, and national security risks of relying on natural gas, which is what we use for this estimate, in our education infrastructure for the next 3/4 century. And so in sum, Ideals is good for Chicago. And what's been good for Chicago has been good for the world 10 times over, which is why we're proud to have presented Ideals, the school to power Chicago's future. Thank you.
You.
If you would please answer briefly, because I'm going to pack a lot in. Why did you choose 8-inch on your bore field? Where is your bore field located? And did you explore the thermal conductivity of the geology?
So GLHE Pro accounted for all of these factors. We assumed they would be located under our landscaping. And we had set up the site and used, we had experimented with different fluids that we would use and then optimize. I forget the exact one, but I believe it was, or I'll leave it, I think it's in the narrative. But yeah, we explored all these factors and then they're all basically built into GLHE Pro. These are all the inputs alongside the capacity demands and the monthly loadings that then generate automatically the depth.
Okay, so working with, did you guys engage with Chicago Public Schools?
Yes, we spoke to them directly.
How did they feel about bringing in these new technologies once it's not common in their school district?
Definitely hesitant, but the UIC factor, the USC partnership with them giving the land and with their PSPM project experience, which we also engage with a lot. We spoke to many members of the PSPM project, especially with how project management team, especially with how they would be able to handle maintenance on these systems, how they would integrate them and keep them going. When we mentioned that to CPS, they saw a lot of feasibility in that.
Okay, one more.
Yeah.
And then I'll turn it over, I promise, guys. The Chicago Public Schools has a lot of deferred maintenance. So why did you go with new construction instead of retrofitting one of their existing buildings? And I didn't necessarily see that difference in that pricing inside of your cost analysis.
That's an excellent question. We wanted Ideals to stand in full range, as in we wanted it to be a real prototype and sustainable innovation that future new construction and retrofits can take full deliberative, inspiration from. And to have that full range, we felt like using materials that justify themselves in terms of carbon cost capture would then enable us to get more freedom with new design to set one, shining example or model that then can be used as a model for a lot of the retrofits. It wouldn't be the same range of action per se with retrofitting existing school, and also because of the UIC location, the UIC narrative push for the school as well. At collaborating on giving access for students to UIC facility and collaborating with the school was a really big part of our vision for this for the school.
Thank you.
Can you,
Please.
can you talk to me about the acoustical system that you designed?
Yeah, I can speak to the acoustical system. So the main acoustical system that we're employing is the panels that are going to be alongside the classrooms of along the walls of all of the classrooms. We also made sure to optimize our flooring as well as the insulation that we used. We chose to use Rockwool insulation, which doubles as acoustical and thermal insulation in the building. We also made sure to optimize our walls towards thermal insulation. If you look on some of the renders, we do have the panels modeled.
You said you have an 8-hour battery, correct? So was that modeled on just the critical loads or what does 8 hours cover?
Right, so the 8 hours is enough to sustain the entire build, like the battery is enough to sustain the building for 8 hours, and it has like a 12 kilowatt, it's like the power is 12 kilowatts. So I think 8 hours is enough during grid disruptions, like the battery is not used like throughout.
So 8 hours in the winter, 8 hours average, 8 hours in the summer.
It's 8 hours average because we're taking into consideration like when there's grid disruptions and like worst case scenarios, we want the building, I think 8 hours is enough to like factor in all the like charging and all the building, like you can charge everything. And then if there's any excess energy, we sell that to like neighboring communities.
Right, but 8 hours average then doesn't mean worst case scenario, right? You understand that, right?
Right. We had to take into consideration the cost and efficiency, and therefore we chose the battery. And also we have all the intricate systems, like, so it's not just the battery that's like helping, it's the AI powered system, it's the microgrid, and the microgrid's connected to like the algae facade, all the prosumers, all the technology that's like generating energy. The battery is just there just in case like all the other energies don't work during the grid disruption.
Comment and then question. I appreciate the optimism of a 100-year lifespan. But that portends two things: that you have to have a high level of confidence in the performance of the core materials and systems. And so it'd be incumbent to include that in an evaluation. I'll have to go back and kind of make a judgment on that later. But the question that I have is an aesthetic that seems genuine and thoughtful, but why only a small portion or a segment of what I'll call a dual envelope construction, and what sort of perpetuated that decision as to how much to encapsulate in that format?
Well, okay, first to clarify, what parts are you exactly like referring to?
Well, there was an explanation of the dual envelope area that had operable fins, I believe, and that there was a portion of the building that was clearly a dual envelope, and then other areas that adjacent to that were singular. And so I'm wondering what decided that balance, and if you did some additional planning or thoughts on performance.
Yeah, of course.
With more alternatives.
So essentially what we did is that we look at the sunlight analysis of our site area, and we noticed that the south facade is going to receive the most sunlight. So there we decide to incorporate the double skin facade because we know that we'll be able to use the sunlight in order to heat the air and create a stack effect throughout our building. We do it across the entire south facade, and because we want to be able to like maximize the degree of the stack effect throughout all of that like area. Then on the north and west facades, we know that there is still sunlight, but we know that it's also a little bit reduced. So it's not going to be as efficient to use the double skin facade in those areas. That's where we incorporate the fin shading. That's going to be like, it's going to be able to like change, it's kinetic. So it can adjust to like the current sunlight situation. On the north facades, we have like rooms such as libraries and offices where people might not need as much sunlight like all the time during the day. And so we're able to use the like kinetic fins to adjust to that situation.
Okay. And to further on that, is there insulation then as a consideration in those various facades, I guess I'll call them, to respond to that?
We use triple glazed windows.
Yeah, and fully flashed and sealed. And then the section that we showed on the south on the cut was the south facade section with the double skin. And it's primarily, we use horizontal shading as well on the south side, but we know that from the orientation of our building east-west axis, we had the south intentionally optimized for PV performance. And so the afternoon sun, or the uncomfortable sun that needs the shading, primarily was the north and west entrance, especially since there a lot of activity goes on there. A lot of our central like hubs and movement is there. And so that's where we prioritize shading. That's also the entrance of the building, and like it's the side that looks at UIC. So the maximum aesthetic value comes in that area. We think the double skin facade is pretty aesthetic as well, but it's also very functional. And so the south facade being the functional area is like, our philosophy is basically the south facade functions well and maintains a high level of like aestheticism, but the south and the north and west need shading and are also the main identity makers of the building. And so that's where we play a little bit with the architectural themes, and that's where we integrate the most like shading catered envelope.
I get the architectural argument on the north facade, but does the north facade actually get that much sunlight? And why didn't you consider the east facade, which for sure gets a lot of sunlight in the morning?
Okay, so the east facade, first he's mentioning the Relux CAD on which we did show results for. So in the Relux CAD, you see that there is a high amount of daylighting that is entering the space, like from the north and from the like west angles, which is why we had to use the fin shading. Without it, we are gonna like create a very overheated space, even with the triple glazed windows. However, we didn't really address the east facade as heavily because there is a building adjacent to us on the east facade. And so the sunlight isn't really entering that area as like greatly. And it's also where we decided to put our gymnasium and other facilities that can't actually have as many windows according to building code.
So the skylights are solid glass, and I know you used electrochromic, or I guess electrochromic. But that's a lot of glass. What was your reasoning? You could have gone with quite a bit less glass, and electrochromic's not the cheapest stuff in the world. I've used it.
Yeah, so I mean, at the end of the day, we do want to we want to create spaces that are fun and that are like healthy for students. And so because it's in the courtyard space, we understand that the skylight is going to be like delivering a lot of light into the courtyard where we have greenery and things like that. But this isn't a space that needs to be like used consistently. And so that heating effect, first of all, could benefit the building because we could use the excess heat to like heat the rest of the building during like winter times, but also because we do optimize our skylights with enough technology. We use the electrochromic, we use triple glazing, we also use low E coatings and krypton gas to reduce the amount of like sun that's going to be entering into the space.
So the electrochromic will reduce the sun, but all that other stuff is going to hold the heat in actually. So in the summer, how are you keeping from overheating? In the winter, it's great, but and maybe the answer is the energy balance is you get so much heat in the winter that it's worth the overheating the atrium in the summer, but that atrium is going to get blasting hot potentially in the summer.
I mean, we also mind that the windows, the skylights are operable as well and connected to our BMS system. So we could open the space up to like create airflow. But then also we know that the average school year doesn't really go into like the time that it would be that hot.
We can do one more question.
Thinking about operations and maintenance and life cycle and replacements, it seemed like that section in your narrative was a little short. So knowing that these buildings have life cycles with their systems, tell me what you did explore and maybe didn't make it into the narrative.
We looked at especially the more like unique ones like the algae facade. We were researching how they actually get maintained and then what are the cycles that they would go through. And then for PV long-term efficiency, we weren't able to delve as like far as I think we would have wanted to just because of the time constraints. But with the PSPM's, I guess, guidance of it, like through it, we mainly got some idea of like how long the replacement cycles would be. And estimates of it are relatively factored into the market analysis cost as well.
I do want to add something with plumbing and maintenance. One thing we did take into account was the tank sizing. And so we did size the tanks pretty conservatively to account for contingency cases in which there would not be like full operation so that we wouldn't have overflow. That's why we size our tanks pretty largely.
Thank you once again, UIUC. Very well done.
Excellent job. Thank you. And a very generous gift, but I'm afraid we're not able to accept it. Thank you.
Yeah, thank you. Next, we will have University of Cincinnati present. Can I please request all the presenters to come up front?
They're outside.
Yeah.
I kept bumping into you.
Cincinnati Mondrian.
Hello, how are you?
Yeah, which one?
I think it's Mondrian, but
Oh, yeah.
you guys are Mondrian, right?
Yes.
Oops, I'm sorry.
You stay here.
Me and Tom will stay on this side, and it'll only
Instinct.
Sam and Elizabeth swap places. Because then you two can just handle the back corner and the boys will come.
Thank you. Okay, I think we're not going to, I appreciate you figuring.
Thank you.
I was just checking. Right.
All right, University of Cincinnati, you can go ahead and get started. Good luck.
Thank you. Hi, everyone. So we are the Mondrian School of Sustainability. We're actually a new building. We're going to be located in Amersfoort, Netherlands. And as you can see in our name, and we are actually inspired by the local artist Piet Mondrian. He was a big inspiration on the community. He was actually born in the same neighborhood as our site. So he was a big inspiration in our design. And so for our design team, we're actually consisted of 9 architectural engineering students at the University of Cincinnati. And what this has done is it's allowed us to gain a lot of sustainable knowledge and a lot of breadth of knowledge in all the topics through our curriculum and our co-op program. So as a part of our senior capstone, we actually have 4 teams here at the University of Cincinnati that are entering into the solar decathlon competition. And so our team specifically is the STEM high school. So we are set to have 200 students and a directed course in alternative energy solutions as a part of the STEM curriculum. And then we're actually going to be open in the evenings for community members to engage with the coursework as well. So with that, Maeve is an example student that we have that's actually going to be attending our school. And the reason we included this was just as an example throughout our architectural portion of the presentation so that you can see what an example student would be like going to this school. So over the climate in the Netherlands, it's going to be a maritime climate. So it's going to be a lot more moderate. We have actually some clients in the Netherlands that we've been working with, and they have reported that summers are increasing temperatures. So that definitely was a big consideration for us to worry about cooling as well. But the main thing that we were considering was heating throughout the portion of designing our mechanical systems. For the culture in the Netherlands, so they actually pretty much bike or use public transport pretty much throughout the country, especially to and from work. They're not really going to be ever driving to and from the school. So that's not really, that was definitely a big consideration for us on a challenge. And then they're also very space and energy conscious. So they actually have the highest solar panels per capita in all of Europe. And this has been great for producing renewable energy. But then the issue is their power grids in the cities just really can't handle all of that. So they actually have excess energy that they have to just unload into the ground and they can't do anything with it. So this has presented a storage option or a storage opportunity for us to really kind of impact the community with some storage, energy storage, that is. So through this energy storage, we actually considered a multitude of options. First was batteries, then gravity, thermal options, molten salt, and CO2. So we've looked at all the pros and cons of these different types of energy storages and decided what would be the best specifically for our site and for the school as a whole.
This image is an overview of the area in Amersfoort where the 4 UC buildings in the Solar Decathlon live. Our student Maeve will take a 15-minute train ride from Utrecht and then a 10-minute walk to our educational building site. And then these are the energy storage solutions that each site has chosen for their various site and program. We chose molten salt for its storage density, and we also use gravity batteries for its visualization and its learning purposes. All of these storage solutions are connected by a microgrid so that we can release that excess energy into the grid and it can be used by any of our different buildings or storage solutions.
So for our general mass of the building, we started with a big box and we split that box into an academic and public side. And then we modified the public side to introduce a walkway from the train station right into the main entrance of the school, the academic side. Then with our required square footage for each space, we stretch and pulled that building to meet those required sizes. And then we tilted all the roofs to maximize that solar gain wherever we could. And then last thing we did was we connected the academic and public side by a sky bridge. And this is how we came up with all those spaces. We clumped together all the classrooms, the gathering spaces, the restrooms, the staff and services, mechanical and shared spaces all together so that all the classes are close by to each other.
This is an overview of our site design. Maeve enters from the southeast side and uses that walkway right into our school entrance. Also, the adjacent neighborhood to the north has easy access to our site as well. The highlighted areas show our over 230 bike parking spaces for our 200 students, along with 5 car parking spaces, 2 loading docks for each wings, and outdoor seating coming off of the atrium. This shows the views on site that informed our design, along with the spring equinox sun angle that shows kind of the average daylighting that we're getting.
And this is our first floor of our building, where on the left side, our academic side, Maeve would walk in through that main entrance and the admin offices are directly off of that. Then going in, Maeve would enter the cafeteria with a grand staircase and 2 labs and 2 classrooms off of that. On the public side, we have our DIY space, which is multi-use, big open space for hands-on learning, and then an auditorium for presentations, lectures, stuff like that. On the second floor, going up that grand staircase, we have 2 more labs and 3 more classrooms. And then Maeve could take that sky bridge over from the academic to the public side. And on that bridge, we have study spaces for all the students to use. And then you can also enter the auditorium from that second floor or go down the steps to get into the DIY space.
So as Dylan and Elizabeth mentioned, when Maeve comes in at the beginning of the day, the first space that she opens up to is the atrium. It is a great social space for students to meet before and between classes. It is also the space for lunch. So after her first morning classes, she would come there to eat as well and socialize. There is both tables and for lunch and stuff, as well as the seating along the stairs. This is meant to be a large social space for all of the students.
And this is a building section cutting through that atrium space, showcasing on the bottom there is our winter sun entering the space, letting all that light get in. But in the summer, we are blocking most of that with overhangs, but letting some come through our skylights. And that is a double panel curtain wall on the side there to maximize the heat loss.
Another space that Maeve and other students would go to is a DIY center. This is not only for the students, but as well as the community. It is a place to actively hands-on learn about sustainable energy technologies. Because of that use of it, we also included our gravity storage in this area as a good demonstration for energy usage.
And this is a building section cutting through the DIY, again, letting that winter sun come in to light the space, but blocking out most of that summer sun.
So Maeve in particular, as well as some other students in her classes, are more environmentally geared because of their course schedule. So she is into the environment. So ideally, we have this green roof for both academic and leisure purposes. Ideally, we would have the students manage and upkeep the plants on this area. It would not only be for a hobby and leisure, but also as well as it would be incorporated into their class schedule. Another place that the students would get to utilize is the Sky Bridge. This is what connects the academic wing and the community wing. It acts as a flow as well as a stopper to separate the two. You'll see that it is a long walkway that offers a great flow for getting to and from classes, as well as a seating area for socializing as well as studying. You'll notice at the bottom, in the floor plan on the bottom, on the right side, there are a couple in quieter study spaces for students to utilize.
And this, we just, to figure out how many classrooms we needed, we made a schedule for the school. We decided to go with a block scheduling system, with Monday, Wednesday being different than Tuesday, Thursday, with Friday being open for general assembly spaces. And the students can pick a path in their later years of school and focus their classes on there. Maeve is, we imagined, as an earth science student. So this is an example of what her schedule would look like.
So one of the biggest things we wanted to consider is not only harnessing daylight through the solar panels that we have on the roof, but also throughout the space to maximize daylight and wellness. So the first thing that we did is incorporate this product called CowWall. It's actually a translucent insulated panel that fits right into the curtain wall system. And what this does is it allows 80% of daylight to get through into these large spaces, but it holds an R value of R20, which is going to be way larger than any glazing that we could possibly have. And it's going to really limit the heat transfer through the walls, as we also have those on the skylights as well to minimize the glare. One other thing that we included was light shelves. So we actually have the eyebrows that you see on this NREL facility that we were heavily inspired by on the south facade of the lab, as well as a light shelf that actually is going to be on the atrium to really maximize the light into that space, especially during the winter. And then lastly, of course, the solar panels. So we actually have this berm out front that's going to block sound from the train station, as well as create like a clear path for the students and give like a really close up view of the solar panels. And with our site, this was actually going to get maximum sun throughout the entire year. And then we also tilted some of the roofs, as we said earlier, to really maximize the gain as much as we could. Oh, and then, sorry, the daylighting analysis we also did to maximize, to ensure that these daylighting strategies were actually effective. So we performed a spatial daylighting autonomy according to LEED and WELL standards. And we actually received 65% of the area to succeed, which does meet all the requirements of LEED and WELL. And we are over on the annual sunlight exposure, but this is because our software was limited with not including that CowWall or anti-glare film that we are definitely going to include. So we are sure that we are actually going to meet full requirements and not have really limit all the glare into the space.
So this is our lighting layout using LED energy efficient fixtures. And also where applicable, we had daylight sensors with dimmable lighting based on our daylight analysis. Here's our second floor. And also we incorporated occupancy sensors.
Here's an overview of our structural axonometric for the school in the DIY space. With the smaller areas such as the classrooms and the offices using a CMU block wall, while areas such as the auditorium and the cafeteria are using the long span steel structure. The school and the DIY are connected through a bridge with a Varendale truss, and we are mainly using recycled steel to help reduce our carbon output. Here's an overview of our plumbing for the school and the DIY. It was designed to the 2018 International Plumbing Code. For our mechanical side, we are using ground source heat pumps to help make our building more energy efficient. And this is just a layout of the piping. And over here, we have ductwork with the heat pumps. We are bringing outside air in through dedicated outside air systems, and we are helping bring in makeup air as well for the exhaust requirements from the DIY and the lab spaces. And to the east of the DIY center, this is our ground source heat pump loop field. Each system is run independently. So if all the heat pumps in the school can be shut off if only the DIY space is occupied. And they each consist of 150-foot deep wells.
So for calculating our energy consumption, on the left, we have our equipment loads expected throughout the year based on occupancy and usage. And then on the right, we have our lighting loads where we tried to adhere to 0.4 watts per square foot for each room.
So this is a breakdown of our energy usage index. So our baseline using Sapphira and ASHRAE 90.1 standards for schools was 46. By utilizing better insulation, double glazed facades and triple pane windows, we were able to bring that down to 23 with ground source heat pumps and occupancy scheduling. So shutting off one part of the building if it wasn't used, we were able to bring that down to 17. And with our 15,000 square feet of solar panels, we were able to bring that down to -1. And our annual energy usage is around 203,000 kilowatt hours per year. This is a breakdown of our energy production per month from those solar panels. So this is a comparison between energy produced and consumed. The bars in green show we produce more in those months than we use, with a big dip in July and August due to school being out of session, and the ones in red show where we use more than we produce. So energy storage is really what we looked at for that. For that, we're using molten salt. So you can see in the orange bar there, the total energy we have stored in our system throughout the year, really getting up to full strength in October. And as we go into November and the winter months, we start using that stored energy, reaches March, then April, we produce more, so it charges back up again, with the excess we produce being sent to the microgrid. This is a breakdown of our carbon emissions based on, compared to all other buildings in the Netherlands, we rank in 311 in kilograms CO2 per meter squared. With most of our materials being sourced locally, 90% of it is in the Netherlands. All of our concrete and reclaimed brick is actually sourced just a single mile from our site.
So when considering the cost, we took into factors such as the material, the labor, cost of utilities, and the design process, as well as precedents from projects with similar scopes, and we estimated about 15 to 20 million US dollars for this project.
Thank you.
My, oh,
Go ahead, go ahead. No.
My burning question is, no pun intended, was, for the molten salt, how are you generating molten salt? Number one. And then number two, how long do you think you could store molten salt before it kind of loses its heat?
So through investigation, we found that molten salt is a high density, high capacity material that can store it for about 5 to 6 months, if not longer, which is what we need it for. And then, so basically using that, any excess solar production is turned into thermal energy that heats up the molten salt. It then, when we need it, cold water gets run next to the tank, gets heated up, turned into steam, which then turns a turbine.
You said turned into thermal energy, so like with resistance electric heaters, or how does that happen?
It would be something like that, yeah. Resistant electric heaters, or the solar molten salt we were looking at has it packaged in the tanks. You just have electricity go to that, and then it is part of the tank itself. But I mean, it can be done several different ways, so.
There's also a diagram on the bottom, I think. Kind of illustrates it's a little small, but kind of the process of how that works.
Yeah.
Why did you choose the Netherlands? And then did you have a community engagement and actually like speak with
Yeah.
people in the area?
So our site was assigned by our professor. We are all seniors. This was our capstone project. He chose the Netherlands because he has some family out there that we could talk to, see what their lives are like, how different it was. And that it was an extra challenge compared to what we're all used to here. And like one challenge on the architecture side was when I first made the floor plans, I had a nurse's office. And I talked to them and they're like, we don't have nurses' offices in any of our schools. So just those culture differences was really good to have someone to talk to.
And then did they provide design influence
Yes.
on what you did?
Yeah, they showed us around their living area, like their house and their neighborhood, and showed us some of the local buildings, and then used that to inspire how our building looks.
Okay, well, you go to your ground source heat pump design in your field.
I got this.
Wow. If you've been sitting in here a while, you know I'm gonna.
Yeah. Go back.
You
back
passed
this guy.
it.
Yeah, you passed it.
Oh, no, keep going. That one source, yes.
This one.
That.
Yeah, I saw in the one before that it looks like that it's off to that east side of the building, right? Did you, over here, right there, right? Did you model those so that you know spacing, diameter of your wells, depth? I mean, I see it's 150 feet to access the groundwater. That's confusing to me. Is this closed loop or open loop? Kind of dig in a little bit more on this one and then go to your next one and then tell me if that's a headering kind of diagram on the next slide. So, oh, one more. There we go. Talk to me a little bit more. I want to hear what you learned.
So essentially with with the fields, it's about 100, you should be going about 100 feet deep per ton of cooling that you'll need. And another one says an adequate amount of groundwater that essentially those heat pumps can just dip down, reach into the water to heat or cool for the space, depending on
It's
the,
closed loop?
yes,
Okay.
yes, it is close.
Okay. And then talk to me about this diagram. Talk to me a little bit about what you learned about the design where you have, you know, a U-bend, what is this spacing and why do you have this connection across?
So like so I'm looking at, so for the school, for example,
Uh-huh.
it's going through there's going to be like five rows of wells, and essentially that is going to go into one well, heat or cool, and if say it's not enough, we'll go into that next well and just keep going. And then same with the DIY, they're both two separate systems, so we don't need, like, for example, if all the DIY is closed, we'll have all those heat pumps off and that won't be active. But the school is occupied, then obviously that field will be running and helping heat and cool the space from the academic side.
Okay, one more question, not on this, letting you off the hook. Let's switch over to the EUI. You said you started at 46 based upon those standards. I'm seeing a lot of program spaces in here that are laboratory,
Yes.
which have more intensive kind of air change rates, ventilation, all of those other wonderful ASHRAE standards that we love. So how did you confirm that your 46 was the place that you should start? And did you model the building itself to determine what your anticipated use was?
Yes, so Sapphira, which is the program we use, we model it in Revit and then pull it in, and then you can.
So that's your model, that's your modeled number.
So we can. and
Pardon
you
my
can-
misunderstanding it. I thought you were taking a,
No.
okay, a reference.
Yeah,
Okay,
you
gotcha.
can,
Thank you.
like, designate areas of square feet as what occupancy type they are. So this
Uh-huh.
is gonna be a classroom, and then Sapphira knows based on that, like, what inputs to put in there to give you a number for it.
Did you, oh, by the way, the architectural design's phenomenal. But anyway, did you look at, so you have those geothermal wells,
Yeah.
good design. I had the same question with the crossovers. I still don't understand that, but you have, who's the structural? Who did the structural?
I did the structure.
So you've got all those right there. You've got all those piles. Did you consider using those piles instead of doing a separate set of,
That's a great question.
right? 'Cause it's
Super
been
question.
done, right? I've worked on a
It
project
has
for
been
Google that did
done.
that.
I did not, because I, by trade, do mechanical systems design. So when I was doing the structure, I tried to keep it as simple as possible. So, I did not really
Guys, you
consider.
gotta
I did
consider
not,
others.
I did not
Considered but
really
not
consider.
pursued.
What?
Considered but not.
Yes,
pursued.
yeah,
Okay.
definitely.
enough, fair
considered but not
I
pursued.
truly appreciate the student that you brought here today, the ties, the dress. I tend to be more of a retail progenitor, but in any regard, let me bring to a question. The molten salt, is that a choice that was then also selected by the other teams that you're participating with?
Yeah, they got a slide on that.
No, so it was not a hard set rule, but a general rule of thumb in our capstone that no two groups should share the same type of energy storage. So as we were looking at things and experimenting, molten salt got us there. So we said, we'll go with that.
That's very cool.
Yeah.
I mean, there's no question about it, but you're answering a question in working collectively. I didn't know if each team had autonomy to come up with their solutions. But it sounds like
Yes.
we did, but
We had
you
autonomy,
didn't-
but we couldn't
didn't-
like have the same
All right.
exact
Yeah.
thing as.
And I-
Run the comparison calculations though, and kind of arm wrestle with the other teams
Yeah.
to say, we want this one and y'all get something else.
So yeah, because
Yeah.
so everybody like really researched into like what actually made sense. So the multifamily building they presented earlier today, they have a building that's about, I think, 13 stories high. It's very high density. Like they have a lot more energy usage than any of the other buildings here. So they chose the sand battery because they could fill it underground in a lot of their site. The batteries were chosen because their units are a lot smaller. And then thermal was chosen by the attached housing because it fit their radiant heating floor plan. So us, the molten salt and the gravity was solely because we were just so limited on our site space that we had to have something that was high energy density. So molten salt was the one that got us there with also excess that we could actually send to the multifamily since they need the most assistance with how large their building is.
I agree that the architectural aesthetic was well presented. The question I have though is, Maeve's dear friend Gerta, who's wheelchair bound,
We have,
does she join her and?
we have we have an elevator on each side.
Okay, you have an elevator.
Yeah.
Okay.
Here and the
education
building, and then there's an elevator.
Yep.
Yeah, so pragmatically, you've met the criteria.
Yeah.
I just think there's a grand atrium or atrium space there. And like I say, it's appropriate for the Nederlands, but I just want to make sure that everyone could enjoy the.
And then let's talk about teachers then for just a second. Are these instructors, do they office inside of these classrooms? And in looking at schedule, where are those instructors supposed
Yeah.
to go for prep time, et cetera?
So how I laid this out when because I thought of that too, like where do teachers go? Every classroom is the teacher's. So the teacher can use it as an office if they so choose. And the schedule is laid out where every teacher will have at least one period during the day with no students.
Okay.
That can be used as prep time. And there's a teacher's lounge on the first floor as well, next to the entrance right
Oh,
off
gotcha.
there.
Yep.
And so that's a space they can go if they just need to get out of that classroom, but still get away from the students. They can go in there.
We had a lot of scrutiny prior when designing this of whether or not such a small school could handle as many students as it
Yes.
needed. So Maeve was definitely put in place to prove that we are capable of handling those students.
Yeah. Yeah.
And what was her age again? I didn't see that in the
She was
or
a
grade,
third year, so junior.
third year. Okay, third, thank you.
This was all presented and thankfully, thank you to us, in largely domestic US standards. But was any contemplation or weight given to using European standards, DIN, that type of thing? As a proof of the site positive?
So from a plumbing aspect, when I did the plumbing, designed a male and a female restroom. And then my professor, who knows a lot about that culture, and then his family, they came to me and they said, we don't really have separate restrooms. So what that meant was basically I just merged the two together, and what you have is stalls that go floor to ceiling. And so that, I guess, is an aspect of incorporating that into how we would design a
I was
project
actually
here.
referring more to performance level.
Oh,
standards,
performance level, okay.
Like code and.
So we design things to US codes because that's
Sure.
what we're familiar with. So the plumbing was the 2018 International Plumbing
Okay.
Code.
And the
such.
ASHRAE standards probably apply
Yeah.
anyway. right?
And architecturally code speaking, they are a lot less strict than US code out there. So designing to US code, we knew that we would meet all of their codes.
Especially in ADA, as you mentioned, they don't really have too many ADA type standards, especially because many of their buildings don't really have elevators that are so old. So that was one of the biggest things we added. So also like you see between the labs and emergency stairwell, considering pathways to the stairs and different like egress paths as well.
As well as the auditorium as well has ADA seating.
Yes,
Yeah.
there is ADA seating in the auditorium.
And then outside there, flow rates and exhaust rates were also assigned from the international.
Yes.
Great job. Once again, thank you, University of Cincinnati.
Thank you. Excellent job.
We will now take a break for lunch and we will regroup at 1:45 p.m.
Thank you. No,
Hello, everyone. Welcome back. After the break, we have Wentworth Institute of Technology presenting in front of us now. You may go ahead and get started.
Thank you. Hello, everyone. We're the Wentworth Institute Solar Decathlon team. Our proposal focuses on the retrofit of the West Roxbury Education Complex, a high school which was built in 1976, but sat vacant since 2018. Boston Mayor Michelle Wu has proposed a site for the relocation of the John D. O'Brien School, a STEM-focused school that has outgrown its current facilities. The existing building is positioned with a park to the west, a pond to the north, and a marsh to the east of the site. While looking at the climate of the site, the wind and solar directions were two of the most prominent design constraints. The south and west directions of the site are unprotected from both wind and direct sunlight, as there are currently no trees on those sides of the building. During our design process, we have interviewed current students of the O'Brien School to gather their feedback for their new prospective school location. Their input included the hopes of more natural light, STEM-focused workspaces, community spaces, and more contemporary features. During our visit to the site, it became apparent to us that the state of the building was in decay. These photos highlight some of the areas that would need the most work throughout our proposed design. The building as a whole is 579,000 square feet, including a 97,000 square foot addition. With the students' input in mind, we chose to focus on reworking the core of the school to better fit the needs of a STEM-focused curriculum. Our primary scope of work is broken down further into 3 zones. Our first zone takes on the existing pool and gym and transforms the space into the STEM wing of the school. The central location of the school will contain program necessary for a STEM-focused school such as the O'Brien School. The central hall is redesigned as a cohesive path of circulation, which ties all 3 zones together. We also added an entry vestibule within the zone to address security concerns within the existing building. In the third zone transforms the existing library into a more contemporary library that will offer students spaces to explore their creativity. Throughout our design, we used frame views, transparency, and natural light as a conceptual idea which allows students to engage with one another between different programmatic relationships. Our organization of the STEM wing was driven by our conceptual values within our design. We chose to organize the grade levels starting with the 9th grade on the top floor and the 12th grade on the bottom floor, where our STEM showcase arena is located. This creates a sense of progression throughout the grade levels that is fostered by our conceptual ideas of frame views, transparency, and natural light, which connects students together within our zones. Following renders were chosen as they highlight these 3 conceptual approaches and help visualize these interactions through our design. Although these ideas can be greatly beneficial in terms of fostering STEM learning, we understand that they may be distracting at times in a classroom setting. To address these concerns, we have used smart glass in all interior glazing conditions. This allows the teacher to flexibly change the level of privacy of their classroom with a click of a button. This rendering shows what a typical project workshop would look like within the STEM wing. We decided to utilize recycled wood wool ceiling panels in these spaces as a sustainable way to design for acoustic comfort. In addition to their great acoustics and sustainability, the panels also store heat, which is released when the temperature drops within the space. Our proposed STEM showcase arena is located in the heart of the STEM wing and allows students on all levels to experience and celebrate their work. We chose to add an entry vestibule to the school to address security concerns within the existing building. The space doubles as a functional gathering space before and after school hours that includes a living machine. This is a perspective from the central hall where much of the building's circulation converges. And this perspective is taken from the media production room in the library, highlighting one of the many creative spaces the library offers.
The following diagrams represent our instances of skylighting in our proposal. There are 4 instances where we use direct lighting to reach all 4 floors of the building, and 2 different instances where we use indirect lighting in areas where light would reach 2 floors of the building. This represents our window assembly, where we use cross metal louvers as a shading device. The window itself is broken into 3 portions, where 1 is fixed and 2 are operable to allow for ventilation. Our glazing consists of double paned argon as well. Utilizing Climate Studio, we analyzed daylighting conditions in one of our 4-story light wells, resulting in an adequately illuminated space. We also use Climate Studio to analyze our interior daylighting conditions, and through this, we have achieved 4 LEED credits with our current design. This sectional perspective highlights the 2 previous conditions, as well as representing the distribution of light through our stem wing. And we took advantage of the westerly winds of our site to implement a passive cooling and ventilation system through the window and skylighting design. This allows for heat to escape through our light wells. We used Rhino to simulate our passive ventilation through our proposed window system, as visualized in this rendering of a classroom setting. And the existing building has an EUI of 202. This large number is due to the building containing no insulation and single pane glazing. Our goal is to convert the building to a fully electric system. We chose to implement 3 glazing conditions throughout our proposal. We are utilizing double paned argon for the addition, vacuum sealed glazing for the adaptation, and Onyx PV glazing for our skylights. The following diagrams depict the existing and proposed exterior wall conditions of the school. And our wall assembly for the addition uses terracotta panels as a relatively cheap and sustainable material to contrast with our existing facade. These panels are anchored to CLT, which was chosen for its low embodied carbon footprint. With our proposed wall assembly, we improved our R value from 4.28 to 31.5. In areas where we are keeping the existing brick facade, we will be insulating on the interior side of the CMU wall. This improves our R value to 19.36 in these conditions. This elevation of the southern facade shows the contrast of the existing and proposed facade conditions. The existing roof has an R value of 14.7, and we approved that R value to 36.8 by adding another layer of insulation to the existing condition. We chose to take advantage of the pond to the north side of our site to install a closed loop water to water ground source heat pump. This system operates at an efficiency of 350%, which greatly reduces the building's EUI. And we are building upon the existing slab to install a hydronic radiant floor system for heating and cooling of our building. Our new dedicated outdoor air system will bring in fresh air while also dehumidifying the space. Calling back to our sectional perspective, the following drawing represents our use of the dedicated outdoor air system and our drop ceiling, as well as representing our thermal floor system, heating system. Boston Public Schools provided us with their annual water usage at the West Roxbury Education Complex. 73% of this usage is accounted for irrigation and restroom use. Through the integration of a rainwater harvesting system, we were able to collect the necessary amount of water to address these functions annually. This perspective represents our living machine entry vestibule. And this sectional diagram calls out the systems and functions of the living machine. The living machine being our functioning ecosystem in which black water will be filtered and is able to be reused by the school.
With these systems in place, our proposed EUI is lowered to 32. This leaves us with the remaining 1.2 million kilowatt hours of energy usage. The remaining energy will be gathered by PV panels on the roof, which account for 19,000 square feet. The other 4,000 square feet will be placed above parking to the building southwest. In addition to these 540-watt panels, we are utilizing Onyx PV glazing in our skylight conditions. This brings our building's proposed EUI down to -0.6 and will have a net return of 1 week's energy gathered by the PV system. The excess solar energy will be stored in a battery system with the capacity of 1 week's energy usage. This emergency energy is important as the school is used as a community shelter. If that stored energy is not used within a year, excess energy will be returned to the grid.
We developed a functional app that tracks the building's functionality. There is both a student and administrative side of the app, which performs different functions. One of these functions tracks PV energy gathered by the building dependent on daily weather conditions. The admin side will house temperature and smart glazing controls. Our design consists mostly of locally sourced materials, thus offsetting the carbon emissions that are associated with material transport. Using the EPIC carbon assessment tool, we were able to predict the next 30 years of carbon emissions of our proposed retrofit of the school and compare it to leaving the building as is. Our proposed school resulted in 4.8 times less emissions than the existing school.
And we were able to achieve a total cost of $289 million, which leads us to a cost per square foot of $499. And this diagram here just kind of depicting all of our systems proposed and will serve as a wrap up for our EUI and cost as well. Thank you. I think we're ready to open up for questions.
Can you talk to me about putting the battery on the roof and whether you check the structural integrity of that and the permitting for putting the battery on the roof?
Well, in terms of structure, we're using a proposed hybrid CLT and steel facade. But so that would be on the existing roof as well as. Sorry.
Also, the space where we're incorporating the battery is currently used for as a mechanical space on the roof, which we're relocating down to the basement level. So that battery system will just replace the mechanical equipment that's currently there. So.
Are your, in your classrooms, are your interior windows operable?
Yeah.
Yeah, that calls back to so there's three portions of the window essentially, and two of those portions, the top and bottom, are operable while the central is fixed. And we do that to allow for
So
more.
exterior and interior both?
Yeah.
Okay.
Regarding those interior partition glass. And then you also talked about the smart glass or diacrylic glass. Did you do any kind of impact on the environmental performance of the building with those switched on at different times of day, different times of year, et cetera, to validate their inclusion?
Well, we incorporated the specifications in our energy modeling. So as an overview, yes, but we don't have any data backing it up in terms of specific times of the day within.
But it is cool.
Yeah, we think although it's a high cost for it, we think it creates such a dynamic space for interaction between the students that we thought would be worth it.
But did you, so there's two states, did you model both states, right? It's like,
Yeah.
you know,
Okay,
clear
I-
state, it performs one way when you darken it. This is
Yeah, that's
is
right.
it electrochromic or is it liquid crystal, the one that just switches like that?
It switches just,
Okay, so, no, isn't that white normally?
I
don't know.
believe when we did our energy modeling, we used it as a clear state.
Okay.
Okay.
Your starting EUI of 202 was that a modeled EUI or did you use data from 2018 before the school closed?
We were provided a booklet of some of the specifications of the existing school. And we also went on a tour. They were Boston Public Schools and they kind of broke down what they knew with the existing building. And that was just one of the biggest concerns they told us was that there's no insulation within the existing building envelope.
Okay,
So
so
we-
you modeled it based upon that book of characteristics.
Yes.
Okay, but didn't confirm kind of the energy consumption with that. Because even with no insulation,
Mhm.
there could have been a thermal or vapor barrier created by the mechanical systems. So did any of that come into play, or did you explore anything about mechanical uses of kind of establishing thermal and building envelopes?
Well, we had actually, when we went on the visit, it was during the fall and they had kind of just started their proposed iteration of the school. And when we'd met with them, there's a lot they still needed to figure out within the building's envelope, but they gave us what they knew currently.
Can you talk to me a little bit more about the proposed mechanical systems to heat and cool the school?
Yeah, so we chose to incorporate a hydronic radiant floor system that will heat and cool the floor of the building tied to the ground source heat pump that we use the pond for. And then for a DOAS system, we chose one that would address the humidity concerns that are associated with hydronic cooling.
So in your radiant floor though, what is your heat source? Is there a boiler in a mechanical room that heats the water? in
So
the-
ground,
Yeah, what is it?
the,
In the pod,
yeah,
I'm sorry?
the heat pump in the
Yeah.
pod,
Okay,
right?
yeah,
I didn't,
yeah, that's,
I guess I didn't see that inside the narrative.
oh, okay, sorry. That wasn't in the narrative, but
I presume that connects to your radiant system.
yeah,
right?
that's,
Okay.
I
Sorry,
think,
Gotcha,
okay.
gotcha.
I thought
So
we
didn't-
said that.
Let me ask you some questions about that.
Yeah, let's
Two
go for it.
questions about that. First is, this is in New England, right?
It is,
Humidity is an issue, right?
it is.
When you're cooling the floor, did you look at condensation,
Yeah.
potential for condensation?
We did in that with our chosen dedicated outdoor air system, we wanted to make sure that it would account for dehumidifying the space.
So you have an
which is-
ERV?
yeah.
Okay. Second question is, you chose to use a pond rather than a ground source.
Mhm.
And based on your calculations, it looks like this is a heating dominated climate. There's very little cooling actually, surprised me. So since mostly you're pulling heat out of the source, is the pond the best solution? Because in the winter, when you're trying to pull heat out, I would have thought the pond water is pretty cold to begin with compared to the ground.
Yeah, I'd imagine that is the case. We decided to use the pond as kind of like a more unique utilization of the site as a whole. And also to the west of the site itself is a capped landfill that is turned into a park. So utilizing ground source heat pump to the west may not have been as easy an option as.
Okay. And it's certainly an easier install, right? Putting in the pond.
Is the capped landfill being used as a energy source or a fuel source?
I don't believe so.
Can you capture methane off of
Yeah.
it?
That hasn't been discussed with us, but it's directly to the west of the building.
It's probably encapsulated, it's nothing. You show one of the, what I'll call remediation approaches to the existing building. Was essentially encapsulating the existing wall construction with an interior basic partition.
Mhm.
Was there any consideration, any assessment of how that was going to affect the existing construction, more particularly moisture and mold?
We had met with a exterior fabricator who went over our design. He said it'd be fine in terms of moisture, but our actual design decisions in doing that was more cost related in terms of just leaving that existing brick facade and just be easier to insulate on the interior of that wall.
Easier, yes, but healthy
More.
also, yes?
From when we met with the consultant, he said that it looked sufficient to him.
So could you go back to that section of the atrium? Yeah. Yeah. So from a daylighting standpoint, you're trying to get light all the way down to the bottom of the atrium, that's pretty tough. It's a deep atrium, right? There you go. That's even better. So kind of was that decision to add a walkway in there? Is there any way, did you consider other ways to do it? And could you get enough light all the way down to the bottom of the atrium?
Yeah, so if you look at the louvers at the top of the skylight, we have them perpendicular in these cases where we have the sky lights reaching all 4 floors of the building to allow for that maximum light, where in conditions where they only reach 2, we have them tilted at a 45-degree angle to have more diffused light reach those. But in terms of the organization of the pathways, that decision was made in terms of the positioning of them, in terms of our conceptual values of being able to look into different spaces and that idea of progression throughout the floor levels that we can go back here. Just highlight some of those interactions between the floor levels themselves.
So, and I noticed you mentioned using that atrium as a thermal chimney to ventilate in the summer. Did you consider doing the opposite, using it as a solar collector in the winter? And
So the ventilation up on the top of the skylights is operable, so the inverse would be able to happen.
is there any way to transfer heat
The heat,
down from the atrium into the classrooms and into the?
I guess that's something we didn't specifically think of when we were designing. In terms of bringing the heat all the way down to the bottom.
I don't know if it would get hot enough. Possibly.
The vestibule was described as a living machine, is that what you called that?
Right.
Did you do any type of analyses to demonstrate the positive or negative impact on building performance of adding this?
So this addition here is on the exterior of the building itself, so it kind of acts as its own building in terms of efficient. It's more of a greenhouse space, I'd say, for the plants themselves. So we did factor it into the energy analysis for the building as a whole, but
And along that same line, the original program included a gymnasium and a pool. The building shell is still intact, or were you just demolishing all of that and then replacing it with that new STEM wing?
so the STEM wing, if we go to right here. So the existing pool and gym are on these 2 levels of this main area here.
Okay.
And they're double high spaces. We decided to add a floor plate to make them each single high spaces. But the idea behind taking on those areas is currently the pool is below the gym. So the vapor is affecting the floorboards above it. So currently it all needs to be redone either way, so.
But the exterior shell of the building is still intact. You're gutting it and mezzanining.
We'd be demolishing the side of the wall and then just encasing it with those STEM classrooms around.
Okay.
All right, we're at time for the question and answers. Thank you once again, Wentworth. Next up, we'll have Illinois Institute of Technology. They'll be starting their presentation at 2:15. All right, Illinois Institute, you may now start your presentation. Good luck.
Welcome and thank you for joining us today. We are thrilled to have the opportunity to present Read at Ed. I'd like to introduce our team composed of two disciplines, architecture and engineering majors. We would also like to thank our professor and industry partners that have helped us along the way. The Read at Project, a visionary initiative aimed at repurposing the former Deet Elementary School, is a vibrant educational community hub in the near west side of Chicago. This project is not just about architecture innovation. It's about breathing in new life into their community while addressing critical social issues. Deet Elementary, located in Chicago's near west side, has stood vacant since its closure in 2013 as part of the largest mass school closure in the US history, where 55 schools were closed down. Despite several redevelopment proposals, challenges like community requirements and deed restrictions have left it underutilized until now. The Near West Side, like much of Chicago, has been grappling with the impacts of the migrant crisis, which began 2 years ago. Since then, more than 40,000 immigrants have arrived to Chicago. Chicago, traditionally a haven for immigrants, is now facing strains of the inadequate infrastructure and resources to accommodate this surge. With nearby schools already overburdened, there's a need for resources and that address not just basic needs, but also the educational and social integration for the immigrant community. So why choose this site? Our choice for repurposing Deeds Elementary for the project was strategic. The proximity to shelters, public transportation, and community spaces make it an ideal location. This site allows us to directly address the lack of educational and social services crucial for nurturing a sense of belonging and community among new Chicagoans. Our area offers a diverse amount of amenities, including a large public park adjacent to our building. Transportation is convenient with 5 nearby bus stops and access to the Green Line train. Within a 10-minute walk, numerous creative venues and galleries can be found. Our goal is to incorporate these elements into our building program to serve and connect to the immigrant community. The REDEP project is built on the principles of sustainability, community integration, and innovation. We aim to transform Deed Elementary into a multifunctional facility that includes educational spaces, job training courses, and social integration services, all designed to empower migrants and foster community connections.
So with the current building, it falls under the zoning area RT4 and climate zone 5A. The EUI stands at 134 kilo-BTU square footage per year, signifying substantial overall energy consumption. The main feature of our redesign is the atrium, which serves as a prominent public focal point designed to attract and engage visitors. This feature showcases a variety of activities and underscores its potential to foster meaningful social experiences within the community. So, the atrium takes place in our north facade, which faces the main street. That's why we chose to put it the main entrance here. In front is the original basketball court in which we kept. However, we did do a few tweaking within the landscaping. Since we removed the original brick envelope of the building, we wanted to reuse these bricks into an engaging play area. So here's a close look of the repurposed bricks brought back to life. The children playing creates a strong connection between the building's past as an honorary design decision. You could also see some of the implementations of the reused bricks within our solar canopy. And into our atrium, it cultivates a sense of community as it opens up the space and have light enter. It's also another opportunity to incorporate growth of vegetations. So we undertook the necessary demolitions of walls and floors to achieve our objective of interconnected spaces. The longer side of the L-shaped building was mostly preserved since we needed these classroom spaces for classes such as English language proficiency, social integration services, and maybe even job training courses. On the ground floor is the designated area for public amenities, hosting events such as volunteering programs, legal services, and even fundraising campaigns. On the second floor, we have an open library and gallery that fosters community engagement that will help address some pertinent issues such as the migrant crisis. These also serve as a buffer space between the transitioning from active to passive programs. And then on the third floor is dedicated to youth-oriented classrooms, and it also includes an indoor play area.
So to achieve our net zero goal, our engineering team has implemented a wide range of strategies and approaches. The schematic diagram that you see here summarizes the overall design strategies, which include upgrading the building envelopes with enhanced walls, windows, and roofs, integrating solar panels and collectors on rooftops for electricity generations and hot water heating, while also implementing mechanical, lighting, and plumbing systems to reduce the overall energy consumption. Here we have thermal images that we took during our site visit. The existing building faced several envelope-related issues, including inadequate installations, poor noise controls, and significant air leakage. In developing the proposed envelopes, our final designs go beyond merely adhering to the minimum performance requirements outlined in the building codes. The existing brick veneer wall assembly has an R value